The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark.
Scientific research was something I never planned to do. I never planned to be do any scientific research at all. And I worked most of my life as a forensic investigator. So I really only did this sort of thing on the side as a bit of a hobby. And when I started looking into it, I was a bit disgusted to find that most of it's a lie. And having worked in forensic investigations, I've seen so much of these lies that I decided to investigate it further and just try to expose a bit of it for the public interest. That's about it. That was my motivation. There was a time when I wanted to get out of forensic investigation and do some teaching. So I did a bit of teaching in some universities, but I found that the corruption there was so bad too that I decided that probably is not a good idea either. And so I went back to what I usually do. And that's how I've continued. But I've kept the scientific research work up in my spare time. That's all I do. I'm not going to devote my life to something which is demonstrable rubbish and make that the centre part of my life. No, it's just a hobby. So many people, of course, have spent their lives doing this sort of thing, and it's just a waste of your life. I've said to it a number of times that it seems to me that these people in astronomy, cosmology and the like don't realise that they're spending their whole careers effectively or analogously to trying to find the next decimal place to a meaningless number. Well, what kind of a life achievement is that? And so they live in fantasy land, and that's what we have now. Physical science, astronomy, cosmology, physics, it's just a fantasy land. And if you want to spend your life in fantasy land, sure, but I'm not one of those.
There's a good argument to be made for the fact that the introduction of careerism into science in the 20th century was when things really went off the rails. Of course, there was a lot of other problems regarding for-profit peer review structures and all of this, but when people started depending upon science as their livelihood, it inevitably introduced false incentives into the production of supporting data for popular ideas.
Agreed.
And it's kind of sad because it used to be the case that science was for a little while during the Enlightenment free from this, but it meant that only rich barons could do science essentially, which is kind of sad also. And I'm not sure what the solution is other than what you're doing, which is find some work that you can get paid for and find a way to do science because you just love understanding how the universe works.
That's true.
Oh, I was going to ask, how is it that you became involved in astrophysics and cosmology? Like, why of all of the possible sciences that you could have decided to upend, why did you choose this?
I didn't really. It was a bad choice. I should have done accounting. Or law many years ago. I would have been better off. But no, I'm trained in science, right? That's why forensic investigation, you need to know some science. So I'm trained in science, and I wanted to do something in teaching. And so I took a few courses in things that I thought would enhance my basic training in science and give me more opportunities to do a bit of teaching. So I took postgraduate studies in physics and astronomy and mathematics and even engineering. So I've got quite a few, although many of my critics like to tell people that I'm not trained in anything. I'm a mere gardener and an odd job man or something like that. Well, you know what? Anybody can have a hobby of gardening. I do. Yeah, but a lot of people do. And anybody can do DIY if they're skilled enough with tools. Yeah, I do that too. Yeah? So just because I've got hobbies like that, what has that got to do with the price of fish? So anyhow, it was just happenstance. It wasn't something I'd planned to do. It was just move into teaching and see if I can get a teaching job because I was tired of working in forensic investigation. But that didn't work. That didn't pan out, and so no big loss.
When you say forensic investigation, what did that look like?
It's I did a narrow view or narrow application of this because it's a broad field, right? I did mostly investigations of injuries and fatalities in workplaces and public spaces for insurance companies and law firms. I'm also a qualified occupational hygienist, and I apply that to my investigation work. On occasion, I've done other things, but like arson, for instance, and a bit of fraud, but primarily personal injury and fatalities.
And how do you figure that the forensic process led you into science? Because it's called forensic science, and so what are the things that you applied while doing this work that translated to what you do now for physics and cosmology?
Evidence-based. If I go before a court and I haven't got evidence, you don't have a case at all. You haven't got anything to argue. So it's the same approach when you're doing science. It's evidence-based. And if you haven't got the evidence or you've got some fallacious argument or manufactured evidence, well, that's not a case.
Demystify Sci is an audience-supported project, which means that we do not have sponsors, we do not have advertisements, and that means that we need your help. If you like the podcast, consider coming over to patreon.com/demystifysci, where you get to support us for just a few dollars a month. And if you support us, you help us make better videos, you help us get better guests, you help us spend more and more time making this project even better for you. If you don't have any spare cash lying around, that's totally fine. Tell your friends about the podcast, subscribe to the channel, leave a comment, come to our Facebook group or our Discord page, come join the community and help us grow Demystify Sci into something that the entire world knows about. For right now, back to Steve Crothers.
The quickest way to lose a trial, it seems like, is to lie to the court in any way,
Of course.
shape, or form.
Of course.
But what's interesting is that in a trial or in any litigation, generally speaking, by the time you go to trial, the evidence is on the table, right? Everybody puts the evidence on the table. And assuming nobody's lying, that does happen and it will lose you the trial. But you still have to construct different stories from the evidence. And that seems like where the logic side, and I know you're really into mathematics, which is essentially a form of logic, you have to prosecute the case based on a particular interpretation of the evidence, which you claim is more logical than your opponent. Would you agree with that?
Well, it depends. If you're talking about a mathematical issue, that's somewhat different because you can have a mathematical proof, and that's pretty well watertight. It's either right or it's wrong. When you've got other things where there are other factors that might come into play, and so you have some opinions then start to come in. You've got an expert in this and an expert in that, and they give their opinions. But in the end, solid evidence will always trump opinions, no matter how many. You're going to have 1,000 opinions that are all different, and you come in with some solid evidence, then it still trumps the opinions. So I always try to go for the evidence and base any cases on that. It's the same in science. I think anyway, it should be the same in science, although it's not the same as I said, in pure mathematics. And for me, pure mathematics it's not an exciting field. It's another fantasy land. It seems to me that mathematicians live their life in fantasy land because mathematics is a fantasy land constructed in their own minds. So Clint Eastwood used to say, you got a legend in your own mind. I don't want to be that either. I like to do practical things. So I've never been particularly attracted to pure mathematics for that reason, although I find it can while away a few interesting hours.
The really nice thing about mathematics is that it gives you an answer at the end of the problem. I always really enjoyed that in school because I felt like I knew at the end of the test how I did on the test immediately. You either can solve the problem or you can't. It's very rare that you would you can make a little tiny mistake, that's true. But generally speaking, there's a right and there's a wrong answer. And that's the really reassuring part about logic and mathematics in general.
Yes, that's true.
When it
I agree
comes,
with that.
When it comes to evidentiary standards, let's see if we can delineate the problem that you found in these fundamental sciences when it comes to the pieces of fact or reality that are used to then construct the theories. Because if science is a trial, and we accept that something went wrong in fundamental physics about 100 years ago, what were the mistakes that were done in the trial that have led us to the place where we are today?
There's a lot of problems with theoretical physics based on fallacies, and that has been carried on now for 150 years, maybe more. And these have led to great edifices of theory being constructed on them. And so there's a lot of people have got their so-called skin in the game, and they don't like to hear or see that what they've built it all on is actually fallacious. And so, and it's multi-pronged. It's not just one error here, one error there. It's multi-pronged. And so I can't say that I've uncovered. Well, I haven't uncovered them all. It's obvious, but I've uncovered some, and that's enough to show that there's quite a lot around now that's actually just a fantasy built on another fantasy. And that's why I've said that modern science, modern cosmology, science, physics in particular, and astronomy, they're just fantasy lands. And a lot of people have built this as a career.
Can you take us back 150 years and help us explore what happened to take the train off the rails?
Well, I have a friend and co-writer, Dr. Pierre-Marie Robitaille. I'm sure you know him. And he introduced me to a problem in thermal radiation some years back now. I wasn't really interested in the topic at the time. Well, I hadn't thought about the topic. Is probably the more accurate way of saying, telling you about it. But and so we started to work on this together on a number of issues. He'd already discovered that Kirchoff's law of thermal emission was false. So I looked into that as well, and we had many discussions over the years about it. And it goes right back to Kirchoff, of course, and that was in 1859. Well, there's a real definite marker where mysticism, superstition, and magic made its mark in theoretical physics, because Kirchoff's law of thermal emission is a very magical thing. It says you take a cavity, an opaque cavity, right? Well, cavity may be just a box, for instance. But he says that irrespective of the nature and form of the cavity, if it's at thermal equilibrium and has a certain temperature, every cavity that's opaque at thermal equilibrium will contain the same radiation field. Well, there's the magic, because experiments being done in his time, they line their cavities with soot, lampblack. It's soot, it's carbon. So in other words, we can state it another way. Doesn't matter what it's made of, this cavity, as long as it's opaque. It doesn't matter what its other form or character is. It'll behave as though it's made of carbon. Well,
it seems like this goes back to like a real desire to universalize. This is the first introduction of I can apply my idea to everything all at once. It seems like the fundamental flaw in Kirchoff's law is the universalization of the theory. Whereas it was tested and observed in a very bounded set of conditions, now Kirchoff has this desire to make it apply to everything, even though he has never observed that.
Correct. Neither observed, no theory that can justify it. He just made it up. And it's become folklore, or more than folklore. It's become fundamental in a lot of physics. And so it's been applied by astronomers, for example, to stars. It's applied in many places, this idea of universality of thermal radiation in a cavity. And Planck comes up with an equation, describes it, that'll only work provided you've got a nice cavity made of carbon. But if it's not made of carbon, Planck's equation doesn't give you the thermal spectrum at all.
And
So
so what is the implication of this though? So you have a law that says that you can evaluate the black bodiness of something based off of this standard spectrum. And so if something matches this spectrum, it's a black body, and that tells you about the structure of the object. And so if your law is
yeah.
mistaken, what is the problem that arises?
Well, first, the problem is a cavity is condensed matter. So only condensed matter can produce a thermal spectrum. There's the first thing. Astronomers apply it to a gas. Well, gases that don't produce thermal spectra. And as Dr. Pierre-Marie Robitaille has made clear, a thermal spectrum can only be produced by the presence of a vibrational lattice. And condensed matter only has vibrational lattice. A gas doesn't have a vibrational lattice. And in the laboratory, no one has ever observed thermal spectra coming from gases. And yet, astronomers apply Kirchoff's law to stars, which they say are made of gases. And then they applied the theory of an ideal gas as well and combine it all. And as a result of that, they end up with problems violating thermodynamics, but they seem to just ignore that, or they don't understand it, and they produce absurdities like negative heat capacities for stars. Put in some heat in the star, the temperature goes down. Take some heat out of the star, temperature goes up.
So with thermal spectra only being possible from condensed matter, I immediately think of the first year chemistry experiment where you take various substances and you burn them in a flame, and then you look at the spectral lines that come out of those substances. Is that not considered a thermal spectrum because it's discontinuous?
No, first you've got to have thermal equilibrium. If you haven't got thermal equilibrium, you're not going to get a thermal spectrum. Right? So that's the important thing. It has to be thermal equilibrium.
In other words, the shell and the substance have to be at the same temperature.
Everything. Yeah, everything's at the same temperature. Thermal equilibrium. If you haven't got equilibrium, then it doesn't apply. Kirchoff's law doesn't apply. So that's the proper statement of Kirchoff's law.
Is it reasonable to think of it as being kind of like a thermal equilibrium is a standing wave that the matter is releasing inside of this container?
No. If you had standing waves inside a container, you've got a resonant cavity. So if you build up a standing wave, that's a resonant cavity. Resonant cavities are everywhere. And this is a simple proof that Kirchoff's law can't be right, because we have resonant cavities. We build them all the time. Well, I don't. Probably you don't either. But technology, we have resonant cavities everywhere. So
just to unpack that really quickly, just so everybody understands, a resonant cavity has no absorption. It's reflective. And the problem with this understanding is that in Kirchoff's formulation and in the subsequent formulations of Planck and so forth, and I believe maybe Stefan and Wien also, you have a situation where the emissivity and the absorptivity are a ratio, and if you have 0 in the denominator...
So what's the numerator and the denominator?
Can you remind me, is it's emissivity to absorptivity, and absorptivity is 0 for a laser, right? Because it's perfectly reflective. You can't divide by a 0 in an equation and have it be valid. So we know that the boundary condition is at least invalid at the extremes. And in the case of recognizing that the law is invalid at its extremes, we don't have a way of understanding where it becomes invalid. At what level of reflectivity does it become invalid? Because it was only tested with perfect absorptivity in these carbon chambers.
that's true. And Kirchoff thought that he could get a special equation that would be universal. Well, Planck gets an equation, but it's not universal. It only applies to a real black body. So if it's not a real black body, then the equation is not going to give you the real temperature. It's as simple as that.
Yeah, I think there's just 2 issues here. One is that he applies it to all substances without having observed it in all substances. And 2 is the actual production of a temperature which relies on clearly violated boundary conditions.
Production of a temperature, you mean the calculation of a
calculation of a temperature, exactly.
Okay, and so to tie this into astrophysics, we have a condition where people are taking Kirchoff's law, which applies only to this specific subset of situations, and using it to look at the stars and then make conclusions about what the stars are and how they behave and what their temperatures are.
Well, exotic temperatures, yes. The thing is, if you look at the spectrum of the sun, for example, you have a thermal spectrum. Now, if it requires a vibrational lattice to produce it, how can a gaseous star produce a thermal spectrum? No gases produce a thermal spectrum. It's a simple fact. The laboratory experience tells us that fact. So the bottom line for that is that when you look at the solar spectrum, as Dr. B. Robitaille has pointed out, it's thermal. Or straight away now you have a proof of the presence of condensed matter. You can't have a gas producing a thermal spectrum. So now astronomers have got a problem because that's their gaseous model is shown to be wrong.
They have two problems, right? They have one problem, which is that they have the wrong temperature because there's convection and it's not this perfect situation like their carbon soot lattice. And then the second problem is that they're able to squirm out of the material nature of what the star actually is because they believe without any empirical evidence that the star can give a thermal spectrum as a gas. So there's two huge problems here, basically. I just want to be really clear with everybody.
Sure. And so the thing that I would ask is, what do those problems imply for the science itself, right? Because I look at it and I'm like, okay, so they're off in temperature and they're off about the structure of the sun. I mean, clearly we want to be as close as possible to reality, and so those are problems, but those feel like easy things to adjust. Is there some other temple of ideas that are built on this that would then suffer if the theory was changed?
Well, everywhere they've applied Kirchoff's law, they've got errors. So, the whole of astrophysics is based on what? Spectroscopy. So you're looking at spectra. So if you can't get your spectra right, what else can you get wrong? You can't. Everything's wrong. So,
like the lives and deaths of stars, even technological ramifications like fusion. We base our fusion technology on how stars work, but if we don't understand what stars are, how are we ever going to nail that technology?
Of course.
Essentially, the entire landscape of astrophysics depends upon these foundational assumptions. So there's no way to overstate how important they are, and I didn't understand this when I first walked into this landscape, but every single topic that I encounter in astrophysics is built on a misinterpretation of thermal photonics.
And I don't want to belabor the point, but I really do want to get to the bottom of, okay, so they make this misunderstanding. To me, it feels like, so you're off about the temperature of a star. Does it matter? Why does it matter that you're off about the temperature of a star? Or is that just the piece of evidence that's being used in the trial to justify that it's incorrect and to justify a necessary shift? Do you get what I'm trying to say?
I mean, if I can just add, I don't think the temperature is the bigger problem. The bigger problem is thinking that you can get a thermal spectrum from a gas, because it enables this whole Big Bang death cult cosmology.
Elaborate on that, because
the Big Bang, the thermal spectrum of the CMB is thought to arise from a essentially gaseous plasma at the beginning of the universe when atoms first appeared. All of that goes out the window if gases can't make thermal spectra. The way that the sun produces its light and stars live and die, and the entire story for the collapse of stars and the death of stars and the birth of stars depends on them being able to thermalize plasma, gaseous plasma. And so these are the bedrock stories of all of astrophysics and cosmology. And if that fundamental assumption is recognized to be patently false, which it quite clearly is by any empirical standard, then the entire stories for 100 years of astrophysics and cosmology have to be reconceived completely. And that's a terrifying nakedness for people to face.
Okay.
Absolutely right.
So then the problem is not that the structure of the sun is misunderstood and then it's limited to something like the structure of the sun or the temperature of the sun. The problem is that these laws that are used for stars are then also applied elsewhere, and conclusions are made on that basis, which have to do with our entire understanding of the arc of the cosmos.
Yes, more or less. Again, Dr. Robitaille has pointed out, since you need a vibrational lattice, the cosmic microwave background has no means of being created by this Big Bang theory. And the other thing is, it's supposed to be a black body spectrum, the so-called most accurate black body spectrum ever measured, the CMB with the Kobe-Furus satellite. Well, the fact that, so where do you get this from? Well, Dr. Robitaille said that, and quite rightly, that since it hasn't been observed more than about 950 kilometres from Earth, the Earth is the source of the so-called CMB from condensed matter. And what's the most likely? It's the Earth's water, because it's got a hydrogen bond. Dr. Robitaille has covered this. So without Kirchoff's law, you don't have a CMB. Your ideas of what the structures of stars are and how they work is wrong. The gaseous model is out the window. And it's a great change in our whole perspective on what these cosmologists have structured as a theory of the universe. Now, it's a very interesting point here or time to mention here that Dr. Robitaille's model of the sun is what's called liquid metallic hydrogen. And it has a particular lattice, which is like carbon. It's a hexagonal planar lattice, and it has the characteristics which match what we observe from the sun. Now, Dr. Alexander Unziker in Germany has just published a book within the last week.
I think today.
Today was it? It might have been today. Yes, but it's very recently. And I've got the title here somewhere. Here it is. The Liquid Sun, A Coming Revolution in Astrophysics. It's available on Amazon. And effectively, it's a detailed discussion of Dr. Robitaille's analysis of the internal constitution of the sun and stars as condensed matter, liquid model, liquid metallic hydrogen. So anyway, anybody who's interested in this can get this book now and read it for themselves to see that this is a really big change in our understanding of the stars and beyond.
Yeah,
So
I hope he'll come back on and talk just about that book.
Yes.
Because we had a wonderful discussion with him the first time he came on the show. And he's just such a careful, and he's a really good writer too. His stories are very compelling. They're real page turners. And yeah, I love Dr. Unziker.
Yes. So, but this book will be, is a very, I can recommend it because you'll get anybody who reads it will get an understanding of what the problems are in astronomy and what changes are going to come. Sooner or later, it's going to come. And that's why I suppose he's called it a revolution in astrophysics, because it is. And of course, the critics that have got vested interest in this standard model business, they don't like it. And they want to keep what they've got because it's their careers and reputations that are at stake, I suppose, and they don't want to face the truth of it. Well, to me, that's not what science is all about, and a true scientist is not going to put that as the primary driver of the scientific investigation, what your career and reputation is. But they do, unfortunately. So it's very difficult then to have rational discussions with people who are convinced that or want to keep the standard model of these things. And of course, the Big Bang business involves Einstein's theories of relativity, and there's another problem. Without the Big Bang, well, where does that leave Einstein's general theory of relativity? On empirical grounds, it's nonsense.
So I want to hear about that line of reasoning, because you worked with Dr. Robitaille on the thermal emission problem. Were you already working on mathematical problems with black holes before that?
Oh, well, in my own case, I started from looking at black holes, which are, it just seemed to me quite ridiculous. because I've got some notes here, and black holes is one of them that I've covered here. So I'll just read you the notes that I've got here. These are just things that I can quote to people. They can go and search it up for themselves once they've got this information and verify what I'm saying is right. So the first thing is, what about these black holes? What's their physical properties? Well, according to the proponents of this idea, a black hole is a finite mass that has zero volume, infinite density, and infinite gravity. In other words, the finite mass is concentrated in zero volume, infinite density, and infinite gravity, but no finite mass has such ridiculous properties. Okay, that's the first thing. Second thing is, they talk about escape velocities of these things. Well, escape velocity is a two-body relationship, and these black hole structures, or these black hole concepts, deal with a one-body universe, a one-body problem. So you're applying a Newtonian idea of two bodies or more to a situation which involves only one body, and then coming up with escape speeds. So I'll just read you a couple of things here that I've made notes on here for people to know. Let me see now. I've got a few things that would be useful.
I wonder how many people this really bothered too. When I was a little kid and I first learned about these and I was crawling around in the basement of the library trying to understand how the universe worked and the stars, I was really, really dissatisfied with black holes as well. But I feel like that's rather anomalous. Like most people read about black holes and they're like, wow, that's so cool. And I was just like, I don't like this. It doesn't make sense.
It doesn't make sense. It doesn't make sense. But of course, it's shrouded in mathematics and it gives the appearance that that whoever's talking about these things knows something. So here's a few things that I've prepared, and I'll read them to you. Now, these are the properties of black holes, as I said. Finite volume with finite mass, that is, concentrated in zero volume, infinite density, and infinite gravity. Now, mind you, in general relativity, gravity is not a force, it's space-time curvature. So you've got an infinite space-time curvature as gravity. Right? So it doesn't matter how you want to call it infinite curvature or infinite gravity, it's still infinite. And infinities and near infinities, I'll come to that shortly, near infinities play prominent places or roles in this standard model. So what we've got here, here's some examples.
And if I might add, the infinities usually indicate, just like in Kirchoff's law where you're dividing by a zero, when you run up against these things in a physical context, it usually means you've reached the boundary condition of your model. Even if your model is predictive in some regime, if you start extrapolating that curve out into the distance and you reach one of these points where there's an infinity or there's something being undefined through a zero being divided by a zero, you've come up against a boundary condition. It seems like astrophysics doesn't understand the concept of boundary conditions.
Because there's the ultraviolet catastrophe, right?
Yeah, that's a great example.
Would you say that that's a case where they ran into an infinity and then instead of just accepting the infinity because it was easily accessible in the laboratory, right? So when you're talking about something like a black hole and you run into an infinity there, it's harder to put it into the laboratory and study it versus something that's like an infinity with a piece of material that you have in the lab that you can actually poke and prod at. And so it leads you to make a more reasonable conclusion where you're like, okay, the infinity is obviously incorrect and we should adjust the theory to account for it. Whereas with black holes, they're so far out there that the infinity is accepted because it's like, well, the cosmos is weird and that must be the rationale.
Same with stars, right? Same thing. You can't go and grab a star and put it in your laboratory. And if you ask any physicist, if you tell them, well, gases can't make black body spectrum, they're like, of course they can, stars do. That's always what you get. And it's like, wait, but you've never been to a star before. What are you talking about?
Well, that's right. Well, physics is based on experiments we do on Earth, right? It's not hypotheses of what physics is thousands or billions of light years away. You can only go on what you do at experiments on Earth. You can't do experiments billions of light years away. So the problem is it's theory gone awry. Theory now replaces experimental science. And so I'm going to read you some quotations here. This is not mine, and this is real. So about the black hole properties, as I've spoken, these infinities and these zero volumes for finite masses. So here we have, for example, in The Theory of Everything, a book. It's written by Stephen Hawking. It's called The Theory of Everything, The Origin and Fate of the Universe. He published in 2002. He says, the work that Roger Penrose and I did between 1965 and 1970 showed that according to general relativity, there must be a singularity of infinite density within the black hole. Infinite density. Well, there's no such thing. This is theory. It's worse than theory. It's fantasy. And it's fantasy masquerading as a theory. There are no such things as black holes, but people have been convinced that they're there because they've been told to them for so long. Even school children now know about them. It's become common parlance. You hear people talking about a money pit being a black hole for their money. All these sorts of things come up now. It's become ubiquitous almost. Okay, so here's another one. In their book, An Introduction to Modern Astrophysics, published in 1996, astrophysicists Carroll and Ostley say this: a non-rotating black hole has a particularly simple structure. At the centre is the singularity, a point of zero volume and infinite density, where all the black hole's mass is located. Space-time is infinitely curved at the singularity. The black hole's singularity is a real physical entity. It is not a mathematical artifact. Yeah, well, it is. It's produced by mathematical nonsense. But he's saying it's real. They say it's real. They all say it's real. In fact, they call this thing, which they call it a physical singularity. You'll find it everywhere. The physical singularity of the black hole. No, it's not physical because it's a fantasy. Here's another one. In their book, Tensor Geometry, The Geometric Viewpoint and Its Uses, published in 1991, mathematicians Dodson and Poston say this: once a body of matter of any mass m lies inside its Schwarzchild radius 2m, it undergoes gravitational collapse, and the singularity becomes physical, not a limiting fiction. And even more, we go further. Roger Penrose recently won a Nobel Prize for what? The robustness of black hole solutions. Really. In his paper, Gravitational Collapse, the Role of General Relativity, published in the journal General Relativity and Gravitation in 2002, Mr. Penrose says this: as R decreases, the space-time curvature mounts in proportion to R to the minus 3 and becomes theoretically infinite at R equals 0. So they're telling us that a finite mass of zero volume, infinite density, and infinite gravity is a real object. No, it's not. There is no such thing. But they play around with their mathematics. Mind you, they commit errors in mathematics, but they think that they don't, and produce this nonsense and call it real.
Yeah, what do they mean by physical, I wonder? It's like, I don't understand what they mean by physical. They say this is physical, right. But what do they mean by that?
Of course, because it's not physical, it's a fantasy. But they're using the word physical. It's what you use the word physical, and it gives it the character of being physical. No, it doesn't. So, another problem with this is escape speeds. I mentioned escape speeds. This is a two-body relation. You take Newton's equation for escape speed, and you end up with one mass in it, right? That's the mass of the body that you're saying something else is escaping from. But to calculate that, you need to have two masses to start with, and one drops out in the calculations, right? So escape speed tells you what? It says that you have to reach this particular speed before you can escape. Otherwise, it'll go up and fall back down. Now, here's something very interesting, quite funny, or if it's not already funny. In an ABC television interview with news reporter Jeremy Fernandez, on the 24th of September 2013, Professor Joss Bland Hawthorne at the Institute for Astronomy at the University of Sydney said this. I saw it on TV myself. Right? That's why I'm making a quote of it. It's so ridiculous. He says this: a black hole, this is what he says in the interview. A black hole is a massive object, and it's something which is so massive that light can't even escape. Some objects are so massive that the escape speed is basically the speed of light, and therefore not even light escapes. Now let's just think about that. Light travels at the speed of light, and the escape speed is the speed of light. And he concludes that light can't escape.
It's also so bizarre because light doesn't have mass, right? It's not a body. Light is an activity. It's not a body. It's just so bizarre to try to treat it like a spaceship that's trying to leave the Earth or something like that.
But the point here is that if the escape speed is the speed of light and light travels at the speed of light, what will light do? By definition, it must escape. He says it doesn't escape on national television. So it's an absurdity.
What does this absurdity allow them to do? Right? So you have the absurdity of the black hole. There's an infinity, there's an infinite density, there's an infinite mass. What is the utilitarian application of this to astrophysics?
No.
Why do they need this in order to continue?
It's part of relativity, they say. It's part of the theory of relativity, and this theory of relativity is something that they cling to for some strange reason, and you're not allowed to say anything wrong, anything in criticism against it, even, no matter how stupid it might be, how ridiculous it might be.
Well, it's also a huge part of the story of the lives and deaths of stars too, right? This is the inevitable conclusion of large mass stars. So it's an important piece of the story that we tell about what stars are and what becomes of them. And that probably plays into what planets are and what becomes of them and these sort of things too.
That's almost certainly true, but the way that I think that line of reasoning goes is that if you have a necessity for black holes in the theory of relativity, then you have to have a mechanism for producing the black holes. And so the story of the life and death of stars is a necessary formulation for the production of the phenomenon that you need for the theory to hold.
Yes.
Okay.
And remember, the black holes, they say, as I just read from a quote, is gravitational collapse. Of what? A star. And a star is, according to their model, a gas. Now, can a gas compress itself? Because that's what effectively they're saying with their gravitational collapse. The star compresses itself and raises its own temperature. Now, how can anything compress itself? It can't. Some external agent must compress something. Stars now are collapsing. They call the word collapsing gravitational collapse, and they use the ideal gas law. And they say, well, it's the gravitational forces between the particles of the gas that causes it to collapse on itself, or in other words, to compress itself. Well, first, if it compresses itself and raises its own temperature, it's a violation of the first law of thermodynamics. You just made energy out of nothing. The other thing is, you're using the ideal gas law. Well, you know what? In the theory of an ideal gas, there are no gravitational forces between the particles. The theory is based on there are no forces between the particles unless they are, or only when they are colliding with particles of the gas and the walls of their container. Otherwise, there are no forces between the particles. So now they're not only violating the laws of thermodynamics, they're violating the ideal gas law, using an ideal gas law with gravitational forces between the particles. That's not right. There are no gravitational forces between the particles in the theory of an ideal gas. The other thing is it's in a container. All the gas laws have been determined by experiments in a container. They've dispensed with a container as well. No wonder they end up with negative heat capacities and violations of thermodynamics, which is what I'm going to come to next, which is an important thing to talk about. What's the fundamental problem with their violation of thermodynamics, besides that one is the first law of thermodynamics, right, is this. It's very simple, but it's evaded the cosmologists and the astronomers for years, century, is this. In any thermodynamic relation, if you have an equation in thermodynamics, it's like any other equation, each side of the equation must have the same units. Everybody knows that. But in thermodynamics, you also have to have the same thermodynamic character on each side of the equation. And if it's not thermodynamically balanced, even though it's got the right units, it's still wrong. So what do we mean by characteristics thermodynamically? It's very simple. Let's think of something that everybody knows pretty well. You're in your kitchen and you have a cake in the oven. and the cake's at the same temperature as the oven, so it's thermally more or less equilibrium, right? And you cut that cake in half. Does the temperature of the two pieces of cake now change? The answer is no. Everybody knows that the two pieces of cake have the same temperature. Now take those two pieces of cake and put them back together. They're in the oven. Go back together. Does the temperature change? No, it doesn't. But what did halve? I've cut it in half. So what did halve? Well, the mass halved. It's a uniform cake, right? So we know that you cut it in half. You have mass is halved. The volume is halved. But what about the area? The area hasn't halved. In fact, the total area is increased because now you've got a new surface. You've cut it in half. Each one now has a new surface. The total area, it didn't halve and it didn't stay the same. So there are three things here. Things that didn't change, things that changed by half, and things that didn't do either.
So in context of temperature, the temperature didn't change, but
That's
the
right.
rate at which the temperature will dissipate did change.
That's a completely different issue. We're looking here at thermal equilibrium. Everything's at the same temperature. You cut it in half. Does it change? No.
So I guess I'm trying to understand, because thermal equilibrium is there thermal equilibrium inside of a black hole? Or the system that we're looking at when we look at black hole, which I will accept is not a thing, right? So, but I'm trying to steelman the mathematics here.
Stars may be an easier example, but of course it isn't, because it's giving off material to the external environment.
Exactly. Okay, so clearly there is a question of mass and temperature relationship that has to do with flux. And so I wonder how that applies to the mistake that they have made. Does that make sense?
Well, it's not relevant to what I'm actually trying to point out.
Okay.
The thing is this. If you take this cake again and we cut it in halves, everything that's halved is called an extensive property. Right? In thermodynamics, it's an extensive property. So we see that mass and volume, for instance, are extensive properties. They must always be extensive, right? Now, the things that don't change in this example are called intensive properties. So temperature. What's another one? Density. The density of the cake doesn't change when you cut it in half. That's an intensive property. Right? Pressure. The pressure in the cake didn't change. So the pressure is also an intensive property. Now, if you take two extensive properties and divide one into the other, you get an intensive property. And the simplest one is density, because it's the mass divided by the volume. Mass is extensive, volume is extensive, the quotient is intensive, density, right? So there are some principles here, very fundamental, simple principles, demonstrated by a couple of 100 years of experiments and our own experience in the kitchen. So these are fundamental things that need to be abided by, and they are contained in the statement of the zeroth law of thermodynamics and the second law of thermodynamics. Because if temperature is not intensive, the laws of thermodynamics are nonsensical, but they are based on this simple property of matter. Right? So now we come to the black hole issue with the temperatures that you're just sort of alluding to. Stephen Hawking wrote an equation for the temperature of a black hole. Now, Dr. Pierre Robitaille and I wrote a paper on this, and we dealt with two things in that paper, the black hole temperatures and the temperature associated with the Unruh effect. Right? I'll mention a bit more about the Unruh effect here in a minute, and it's very interesting because you recently interviewed Dr. Mike McCulloch at the University of Plymouth in England, and he proposed some theory about quantized inertia, and he invokes the Unruh effect. Well, the problem here is the Unruh effect, like the Hawking equation, violates the zeroth and second laws of thermodynamics. Now, neither Mr. McCulloch nor Mr. Unruh understand that because they are oblivious to the character of intensive and extensive properties, and this is the characteristic of all astronomers and astrophysicists. Now, let's go to Hawking's equation. It's engraved in his tombstone, and he's buried in Westminster Abbey, I suppose, right next to Isaac Newton. Now, this equation now has become famous. It's become something saleable. They even sell medallions and things and T-shirts and all things to the Hawking Foundation in this business. Now, you look at his equation, it's got temperature is inversely proportional to mass. So in other words, if you halve the mass of this black hole, you double the temperature. Well, I might object, you say, oh, well, the theory says you can't bifurcate. Okay, let's take two black holes. They're at the same temperature, the same mass. Doesn't matter if they're not the same mass, but the same temperature, put them together. But if we make it the same, it's an easy number. So if you double the mass, you've just halved the temperature. And we've seen that that's a violation of the 0th and 2nd laws of thermodynamics because temperature must be intensive. Hawking's temperature is not intensive. His equation, even though it's got the same units on both sides, it is thermodynamically invalid and the equation's rubbish. Now, we come to the Unruh effect. Now, I'll read you this because I'll read you this from our paper. This is what Mr. Unruh and his colleagues say. And here we have it. Now, according to this theoretical effect, right, from the point of view of an accelerating observer or detector, empty space contains a gas of particles at a temperature proportional to the acceleration. In other words, if you're in Minkowski's so-called flat space-time and you're an observer or a detector and you accelerate at a uniform acceleration, the background presents as itself, as I said there, which is a quotation from, I'll just give you the quotation from Fulling and Matsis of 2014 in Scholapedia. You can get it online. And that's effectively what it is. You accelerate, the background then becomes this gas of particles at a temperature.
It's thermalized, right? You should
thermalized,
see it.
correct. And it supposedly emits at a black body radiation. Well, first, it's not condensed matter. So we know physically that that's impossible. Now, Mr. Unruh himself says in his paper published in 1976, he says this: these results are independent of the means used to accelerate the detector, but depend only on the acceleration itself. Applying these results on particle detectors to the black body or the black hole evaporation problem, one finds that for a detector stationed near the horizon of the black hole, the transition probability of the detector per unit time can be calculated in a similar way to that for a static detector in Rindler coordinates. And it goes on, then Fulling, I think it's Fulling, I'll just check that again to go on. Yes, it's Fulling and Matsis again. They say in relation to what I just quoted from Unruh, at a small distance, close to the black hole's event horizon, which is well defined without reference to accelerated world lines, the thermal effects can, however, be attributed to the acceleration of the curves of constant Schwarzchild radial position, whereas a freely falling observer there sees approximately cold empty space. He quotes Unruh 77 and Fulling 77. And this is the origin of the thermal emission or ambience as viewed from afar of black holes, as already emphasized by Unruh's original paper, and that's Unruh 1976. Now,
can I just clarify really quickly, just so people don't get lost, that this word thermalization, it doesn't mean what it sounds like. It just refers to that perfect Planckian black body behavior that happens in these soot-covered chambers. It's not just talking about heating up a gas or heating up whatever you want. It's a particular form of radiation, and it's a real tragedy that the language used is thermal because it's a very particular kind of thermalization, actually.
Correct. Now, so the point I'm making now is, well, that means the Hawking and the Unruh temperatures are basically the same, just as they've said. Hawking's temperature violates the laws of thermodynamics. Unruh's temperature violates the rules of thermodynamics because his temperature is not intensive. So he's in violation of the 0th and the 2nd laws of thermodynamics. Now, Mr.
And they're predicated on the universalization of Kirchoff's law.
Of course, because they use this, they effectively use Planck's equation to generate their temperature expressions, right? Because they use the black body concept, which is Kirchoff's law, and that's false. So now I will read you something very interesting, because I wrote to Mr. McCulloch about his interview with yourself when he raised the issue of Unruh effect in his theory of quantized inertia. Now, I wrote to him very recently, it's the 21st of May this year, and I copied it to Mr. Unruh and yourselves. You probably recall it. So I'll read it for the viewer, of your listeners and viewers.
I love
Dr.
how
Michael
much
Culloch, University of Plymouth.
I love how
Yes,
much
sir.
this feels like a lawyer making an argument.
Well, it's evidence.
I appreciate that. I love it.
That's how it works. It's what I do that's how I did things. So I don't see any difference here. And this is from, so I wrote to him in his email address at the university. It's a professional conversation here, right? I wrote, "Dear sir, I've watched your interview on demystifying science, quantized inertia, Mach, and interconnected atomics. Your theory invokes the Unruh effect. Some years ago, I sent you the paper below, which proves that Mr. Unruh's theory is entirely false because it violates the laws of thermodynamics by making temperature non-intensive. I also sent it to Mr. Unruh. Temperature is always intensive. Any theory that makes temperature non-intensive is false for violation of the zeroth and second laws of thermodynamics." Now, the paper that I cited was this. Myself, Crothers S.J. and Robert A.P.M., Bekenstein-Hawking black ball entropy, Hawking temperature, and the Unruh effect, insight from the laws of thermodynamics, published in the journal Physics Essays, volume 33, 2020, with a link to it on the Vixra site. That way he doesn't have to pay for it. Otherwise you'd have to buy it from the journal. I invite you and Mr. Unruh to address the matters raised in the above paper. Yours faithfully, Steve Crothers. Okay. 4 hours later, now that was at 4:11 a.m. my time, so I was up late. On the same 21st of May, at 4:47 a.m., I received an email. Well, it's a pretty short time. I sent it at what time? 4:11, and I received it at 4:47. Mr. Unruh replied. Never replied to me before. He gets this one. It's from his university account, so it's a public document. Here it is. Everyone can see it. It's from him. So he says, well, what he didn't say much. He gave me one sentence. And he goes into the middle of my letter and he says here, and I'll read it, except that because I remember I said that it violates the zeroth and second laws of thermodynamics. He says, except that they obey the zeroth and second laws. If you think on that, you might learn something. Well, he's pretty smart. You want me to learn something. When he is the one who is in violation of the laws of thermodynamics, the zeroth and the second laws, because his temperature is non-intensive. That's it. It's over. Now.
Yeah, no wonder this guy won't talk to us.
No, yeah, that's who he won't talk. Now, on the May 27 or 21, the same day at 6:13 a.m. What's that? A couple of hours at the most. I receive a reply from Mr. McCulloch. He gives me a one-liner as well. He says, empirical evidence for fooling Davy's Unruh radiation, and a link. Well, you know what? One paper claiming that they've managed to experimentally show the Unruh effect is true. What? Against 200 years or more of thermodynamic experiments by a vast array of scientists in a vast array of experiments with some theoretical thing that violates the laws of thermodynamics. No, you didn't. You didn't get such a thing. And that was his response. No.
What do you make of that paper?
Pardon?
What do you make of the evidence presented in that paper?
The evidence, it does not actually verify the Unruh effect at all, and it can never do so for the simple fact that means you would have to violate the whole of thermodynamics. Well, that's not going to happen.
Well,
I'm just curious how does the paper justify it? Do you understand was it an experimental work or was it just purely theoretical?
Supposedly. But you see, they claim that they've also observed black holes and gravitational waves, things that don't exist. I'll come to them shortly. I've got notes for you on this. But you see, I recall that you then wrote to Mr. McCulloch and Mr. Unruh and myself, inviting us for a three-way discussion on this particular topic. And I replied that I'd be very happy to engage in a discussion with both of those gentlemen. And neither of them bothered to reply to you either. So now, instead of discussing this issue, they've gone silent. And why? Because it's clear that they are in violation of the laws of thermodynamics and they don't want to admit it. And not just for themselves, but for the whole of astronomy and cosmology, it's a major blow because everything that they've done with temperatures is a problem.
It's hard to blame them, though, right? You're asking them to martyr themselves, essentially. I mean,
I'm asking them to tell the truth.
Well, yeah, but it's obviously sacrificial to their entire career if they do that. It's just the cognitive dissonance borders on psychopathic levels of devastation at that point. Like, you're going to just destroy your entire life, essentially. I don't know how you can switch teams in midstream like that in the present institutional structures without martyring yourself to this discovery. I'm just not surprised they don't respond. We have anytime that we've had a physicist on this show and we put something in front of them that is an explanation to a problem that they say has no explanation or is some contradiction to the interpretation they're giving, they usually won't talk to us ever again.
No.
And I don't really have any resentment towards them for that. I understand why. I mean, what we're asking is too much in the context of having kids to feed and a house with a mortgage and having a career after you're getting ready to retire. Maybe I just don't know how in the world we can expect these people to do anything other than leave or die and let somebody replace them with better ideas.
Well, I suppose it's up to you. The individual has to choose. Do you want to tell the truth or do you want to hide it? Personally, I won't hide the truth. The truth is what it is. It needs to be known. So if you now know the truth and then you deliberately take measures to hide the truth, to me, that's making things worse.
That's the quickest way to lose a trial too, right?
Exactly.
Lie to the court and it's all over.
Lie to the court, exactly. Now, that's my approach, right? So as I said, for me, I don't waste my time on this baloney, except as a part-time hobby. Because if I was to waste my life on this, I would get to the end of my life thinking, boy, I just spent the whole of my life trying to find the next decimal place to a meaningless number. Great. Anyhow, we can go on because the temperature issue is very important. We go now to the mass luminosity relation of Eddington. This has a long history, going back to 1923. Eddington was given this, or has this reputation of being this great genius. Personally, I think everything he touched, he ruined. Now, his mass luminosity relation, he's supposed to have, you've got a relationship, you've got a mass and the luminosity related to one another of stars. And he used the star Capella, ran his curve that he plotted, go through Capella and using Capella as a reference, if you like. But the bottom line is that when you analyse it, which I've done with Dr. Robitaille, here's our paper. I'll read you the title. It's Eddington's mass luminosity relation and the laws of thermodynamics. It's authored by myself and Dr. Robitaille. It was published in Physics Essays in September, 2019. And here we show, without any shadow of a doubt, that Eddington's mass luminosity relation leads to a temperature via the Stefan-Boltzmann law, which is thermodynamically correct. Eddington's relation for temperature is very simple. You divide his luminosity by the area of the star, then you've got a statement of the Stefan-Boltzmann law. But his temperature is non-intensive, which means it's in violation of the zeroth and the second laws of thermodynamics. So his mass luminosity relation is false. Now, that doesn't mean that there's not a mass and luminosity relation, perhaps, on empirical grounds, but certainly Eddington's theory of mass luminosity is nonsense. And even James Jeans back then raised objections, and he said that the mass luminosity relation of Eddington is a mathematical trick. Well, James Jeans didn't realise this issue of intensive and extensive properties, but he was right in the sense that it is a kind of mathematical trick, and therefore it's just nonsense. But now the principle is easily proven with intensive and extensive properties. A non-intensive temperature for Eddington, his theory is rubbish.
It strikes me as another example of this desperate attempt to universalize this theory of
Yes.
everything mentality, where, yeah, there may be a solid mass luminosity relationship in some subset of stars that would make sense to some extent, but then trying to generalize that law to all stars and to all of these astronomical bodies, well, luminous astronomical bodies, that's where you run into problems, because it becomes foundational that the generalization is true, and you end up with these bizarre cases outside of the boundary conditions, which are quite clearly violations of the terms of the theory. But you take them as bedrock and build more theories, and you do this theory stacking process. You know, there's a term for this in the medical industry called medical anchoring, which is quite fascinating and the source of potentially a lot of death in the medical industry, which is where somebody comes in with a disorder and the initial intake crew sees some presentation of symptoms and says, okay, well, this person's having a heart attack, let's say. But it turns out they weren't having a heart attack. But the people who process them down the line, no matter how skilled their expertise are, they tend to rely upon that initial assessment, and they'll build these treatment programs based on initial errors without revisiting the fundamental facts. And it's a huge problem in hospital systems, and the estimates of, I don't have the statistics as usual, but the estimates of the death that result from this are extraordinary and very troubling.
Yes, that's quite right. I've come across some such information in the course of my career working in forensics. So yes, you're correct. But the thing is, as you're saying, in relation to this physical matter, is this obsession with universality. Everything's got to be universal. It's like, but this is now moving away from reasonable analysis and physics into wishful thinking and fantasies. So in other words, it's mysticism and superstition and magic in a way. And it's become something that's now fundamental to physics. So the whole lot of it now is just building upon this fantasy into greater fantasies, if there's such a thing as a greater fantasy. You know, once it's a fantasy, surely it's just fantasy. You know, and it goes on. So physics needs to be revisited, restructured, and taken away from these people who have just gone off into these fairyland. For whatever reason it drives them, I don't know, but science can't tolerate it any longer. It's got to stop. It's got to change. You know, so
it's really ugly too. One of our patrons made the astute point to me that astrophysics and cosmology really feel like a death cult. If you read the headlines, it's like headline after headline concerning the universe is going to evaporate when the black holes eat everything. You know, even the names they give these things, dark energy and dark matter and black holes, it's like, it sounds like some evil villain shit. You know, it's unbelievable how anti-human the entire project's mythological tone is. And that makes me deeply suspicious of the internal state of the people that are promoting these things, right?
Well,
it's not we have a serious, regardless of what your politics are, we have a serious cultural issue on Earth right now, which tends towards the anti-human, right? Everything is pointed at humans are bad and we're a plague on the Earth and all of this. And I think this cosmology feeds into that mentality. And I think it's really making people sick around the planet. So I think there's a metaphysical dimension to this which can't be ignored, which is popular, especially among the powerful institutional actors, and it's really, really bad for us as a people.
It is. I agree. It seems to be this obsession with what I might call the dark arts. Everything for cosmologists and astronomers is black. Black holes, dark matter. You know, everything's black. So I don't know what their mentality is, what the problem is with them, but I'm just talking about this silly physics and try to get people to realize in very simple terms, like with the cake in the oven, how can these people just violate simple laws of physics like that and get away with it? Here's another one of it. It's very important again with the temperatures. There's a theory of the solar wind. Yeah? Now I wrote Dr. Robitaille and I wrote a paper together on it. Here it is. This was published again in Physics Essays in what year? It was published in December 2018. And its title is Dynamics of the Solar Wind, Eugene Parker's Treatment and the Laws of Thermodynamics. Now, Eugene Parker, the Parker solar satellite is named after him. And we analysed his theory and we find an equation for his temperature. We give it in the paper. And you find in there, he's got temperature non-intensive. So again, his theory is false. And here it's very glaring, is that he has a term on the right side for his temperature. It contains two things. Now, the temperature of an ideal gas is related to the RMS speed of the particles, a half mv squared, where the v is the RMS speed, right? And it's equal to what? 312 kT. So you see there's a relationship between the energy, the kinetic energy of the particle, of the ideal gas, and the temperature. So he's got a term there in his equation. It comes out a half mv squared, where m is the mass of the hydrogen atom, right? And he modifies the temperature with the potential energy due to gravity. Well, first, the potential energy due to gravity is not intensive. So he's modifying the temperature of something that is intensive by something that's not intensive. So that means it's a violation of laws of thermodynamics. The second problem is that it's gravitational potential energy. Gravitational potential energy can't change the temperature of anything. It's potential energy. It's not going to change the temperature of anything. He can't change the temperature of his gaseous solar wind using the gaseous models of the stars, and that equation, therefore, is in violation of two things. Potential energy can't do it, can't be related to temperature, and it's not intensive. It's not intensive to start with. So his theory is wrong.
You know, we had Nikki Fox, who was the director of the Parker Solar Probe, on the show at one point.
Yes.
And something really strange appeared to us in that conversation, which concerned this conversion between the kinetic energy and of these particles and temperature itself, because Anastasia asked the question, how is it you can get this probe so close if the temperature of the atmosphere, the corona, is millions and millions of degrees? And she said, well, there's just not that many particles. So what she's saying is that if you have a room with one particle that's flying a gazillion miles an hour, the average temperature of that system is really high, but it's not going to be a warm system, right? Which really stretches the concept of temperature to the limits at that point, because it's like, what are we even talking about then?
Well, Dr. Robitaille has addressed this issue too, the so-called millions of degrees of the millions of degrees of the corona is not true. Right? You're getting further from the sun and it's getting hotter. So it's not true. And it's because of a misinterpretation of what they're observing through their spectroscopy, essentially. So they don't understand what they're looking at. And Dr. Robitaille is an expert spectroscopist. So he knows how to interpret spectra and what's line spectra, what's thermal spectrum, right? And what mechanisms, chemistry here. He's pointed out numerous times that we have chemistry here. It's not just physics. There's chemistry happening here in the sun and in the corona, and that is what's giving you these effects, and it's not temperature. And they misinterpret it as temperature. So I urge people to go and read Dr. Robitaille's paper on the 40 proofs that the sun is condensed matter. It's available online for free. You can get it from the VIXRA site. And it was published in a journal called Progress in Physics some years ago. And it's very interesting reading. It's a long paper, but the evidence that he presents is overwhelming that the sun is condensed matter. And you will find it's too detailed to go into right now, and I'll leave it to viewers and listeners to go there if they wish to go and get the details. But it's something that you should read if you're interested in this, and you'll find that the evidence is overwhelming, and it's impossible for the sun and the stars to be gaseous globules. It's nonsense.
Yeah, if I could just point out also, there's another work that Pierre did, which I think is absolutely a must-read for anyone interested in these subjects, which is his historic analysis of the debates, because most people aren't aware that the material basis of the sun was under heavy debate for most of the 19th century and into the 20th century. And then people just moved on after this Eddington business occurred and after relativity and all of this. But it was never really decided, is the bizarre thing, right? You have even Kirchoff himself sort of flipping sides at the end, and people just really on the fence about the material composition of the sun, and then they just move on. And so Pierre does this incredible historic analysis in Progress in Physics, which is just a wonderful read, and you really get the scientists operating at the time, you get their own words. He's translated some of these documents from other languages too, so you can read the scientists who are arguing about this in their own words and get the picture of how uncertain the landscape was before everyone moved on for really no apparent reason other than the constellation of facts that led mathematics to interpret boundary conditions as physical phenomena.
Well,
Yes.
isn't the motivation for moving on the entire existence of astrophysics as a field? Because if you're saying that it's impossible to look out onto the cosmos and to make discrete conclusions about the things that you see because you don't have enough information, then you can't really have an entire scientific discipline that's based on that.
Yes, that would be true. But the thing about it is, if you look at the spectra properly, you can gain a lot of information. For instance, just looking at the solar spectrum itself, we see it's thermal. Straight away, we say it's condensed matter. Gases can't do it. Now we've got a proper basis for the sun, as Dr. Robert has pointed out. We ask the question, what kind of condensed matter can it be? You've mentioned Dr. Robitaille's historical analysis or historical coverage of how it came to what it is. And you see that many scientists back then thought that the star or the sun was actually condensed matter. James Jeans argued for liquid sun. Well, liquid metallic hydrogen is the model that Dr. Robitaille has provided. You will also find in some of those historic discussions that scientists were trying to put something like carbon on the sun because of the way the spectra look, right? That's condensed matter. Why carbon? Well, it resembles what we see in experiments on Earth with carbon. And Dr. Robitaille's model with the liquid metallic hydrogen model is it has a similar kind of molecular structure to carbon. You've got a hexagonal planar structure. So it has the right lattice for producing what we see from the sun and accounting for many other aspects that we observe with the sun. Whereas the astronomers with their gaseous model are putting band-aids all over their theory with all sorts of ad hoc arguments, trying to make it work. And because they believe it, they want to keep it and they don't want to change it. Why? That's a psychological issue, and it's something I don't care much about. I'm only interested in the physical evidence and the theories that are behind it all, especially with things like mathematical analyses. You know,
I think it's also worth pointing out that the very, very first records of anything approximating a scientific interpretation of the sun, that is anything other than it being a deity, all imagined that the sun was some sort of really hot rock, right? It looked like a meteor to the first people that when they first observed meteors and found these worn pieces of rock on the ground, they were like, "Oh, that's what that is." And that was a foregone conclusion for a very long time before before the advent of the telescope and sunspots and the idea of the atmosphere became apparent and things got lost. And I also think it's worth pointing out that, you know, James Jeans was a absolute juggernaut in astronomy, but he made one mistake that got him in a lot of trouble, which was that nobody knew how the sun was powering itself, essentially. And Jeans hypothesized that it was radioactive materials that were doing fission, and he was dead wrong about that, and he didn't have an explanation. So when Eddington stepped up to the plate and provided this ideal gas law explanation for the powering of the sun, everybody was just like, great, let's take that instead, because they knew the sun was hydrogen all of a sudden, and they didn't know that until the end of the debate. Right.
That's correct. Yeah, right. So, but so anyway, so you see that the importance of what are we talking about here? thermal emission, very important, the character of temperature, thermodynamics, well-established science, how they impact on all of this, just these two things have such a great impact on astronomy and astrophysics across the board. Right? And of course, you'll find more as you dig deeper into physics and technology, because as we mentioned earlier about resonant cavities, that proves that Kirchoff's law is false. Because if Kirchoff's law is true, you could not build a standing wave, could you? Because the radiation would be absorbed and thermalized and then re-emitted by the walls. So how would you build a standing wave? You could not. There you go, straight away. So the fact that resonant cavities exist in technologies proves that it can't possibly be right.
I wonder. Go ahead.
Yeah, go on. No, that's all right.
I was going to say, we mentioned a while ago the importance of black holes for the theory of relativity. And I wonder if we couldn't trace that out a little bit better for my sake and maybe for the sake of other listeners, because I don't totally understand why relativity requires black holes and why that caused such a long time of justification.
Well, it's a mathematical thing. The theory of black holes is allegedly due to a solution to Einstein's field equations, first provided by Carl Schwarzchild in January 1916. In that time, Carl Schwarzchild was in the German army and was at the Russian front, dying of a disease, solved Einstein's field equations in what Einstein called the absence of matter. And this equation that you see in the textbooks attributed to Carl Schwarzschild is not his equation. Not at all. If you look at his original paper, you find that it's quite different. The form of the expression is there. However, you cannot get a physical singularity from this. There is no interior in his solution. And in I think it was December 1916, David Hilbert came along and made a big mess. And he allowed Schwarzschild's solution, he modified it effectively to allow it to go down to what is now called the physical singularity. Well, that was impossible in Schwarzschild's solution. And Hilbert did this by an analytical means. He wasn't thinking geometrically. I've explained myself in a video, and in a video with Sky Scholar, Pierre Robitaille's platform, that this mathematical gymnastics that was first committed by Hilbert involves this. You take a sphere centered at the origin of a coordinate system. That's the center of the sphere is at the origin of coordinate system, right? And if you move that sphere away, you take its center with it, right? Just like you have a circle in the plane, in ordinary geometry, it's a circle in the plane, it's centered at the origin of coordinates. You move the circle, takes the center with it. And then the origin is there, but it's not at the center of the circle, it's not at the center of the sphere anymore. Now, in the analytic means by which Hilbert incorrectly modified Schwarzschild's solution, he moved geometrically, he moved the sphere, it's involved the spherical surface, away from the center, away from the origin of coordinates, so it takes its center with it, and it's somewhere else. But he didn't realize that, and neither have his followers. So they think that the center of the sphere where it is now is what's called their event horizon, and that the origin of coordinates is the physical singularity, when in fact, the origin of coordinates is not the center of symmetry anymore. You see? That is the geometry that's happened here. So now they think they've got two singularities. One at what they call the event horizon, which is actually the center of symmetry, and another at the origin of coordinates, which they think is still the center of symmetry, owing to Hilbert's error, right? And because it's analytic, they've not really realized what they've done with the geometry. So that's how you generate a black hole. So it's a violation of geometry. even though it's produced by general relativity. That's why I've said in the past that black holes are not actually consistent with general relativity, because it's a violation of geometry, assuming, for the sake of argument, that general relativity means something and Schwarzchild solution means something. You cannot now get a black hole from it because that would violate geometry. Okay? And I've given an analytic solution to this. The technicalities are not that important.
Hold on 1 second. I'm caught on this idea of the center of the sphere moving to the event horizon and the axis of symmetry remaining at the center of the black hole, because when I think about an event horizon in terms of the physical representation of it,
yes.
Isn't it a spherical shell around this theoretical point of infinite mass and infinite density?
Infinite density, finite mass, infinite density, infinite gravity. Yes, well, think of this. The center of their black hole is located at the origin of coordinates right? Now, in Schwarzchild solution, it is centered there, but it's not a black hole. He doesn't have an event horizon in a different, he doesn't have event horizon and physical singularity, right? Now, in the analytic analysis that Hilbert did, the geometry behind it, he didn't see. And what he did was he effectively moved that sphere away, so the center of the sphere is on the origin. Now he moves the sphere away, it takes its center with it. That center of that sphere is no longer at the origin because the sphere has moved away. But the origin of coordinates is still your reference point, right? So the center of the sphere is some distance away from the origin. Now, in Hilbert's analysis, people have come to believe or think that the place where the sphere is now located, because they don't realize it's been moved, they get a singularity there in the equation. And they think, well, we've got two singularities now. We've got a singularity here and a singularity at the origin. Well, the reason is that you got now two is because the center of symmetry and the origin are no longer the same. So they've misinterpreted the center of the sphere that's been translated away from the origin as an event horizon, because they want to make the origin of coordinates still the center of symmetry when the sphere is no longer sitting there.
And the consequence is that you have a volume of singularity now, I think.
I'm just
the entire inside of this sphere is a singularity all of a sudden.
But the sphere, if there is a sphere that is encompassing a singularity,
yes,
then that singularity is still at the center of the sphere.
And the rest of the volume becomes singularities as well.
Okay. So what I'm just trying to I have such a literal mind that I understand that this is, by its very nature, an absurd theory, but I'm trying to visualize the geometric transformation that's happening here so that I can understand the mistake. And so, if you have a point which is spherical, and you say that that is your singularity, that's the heart of the black hole, you're saying that there's a geometric transformation of that sphere away from the center of the black hole to what's called the event horizon. But the event horizon is, as far as I can visualize it based off of all of the artists' interpretation of black holes that I've seen, the event horizon is a spherical area of space that centers on the origin of the black hole, no?
Yeah.
Yes, on the center of symmetry of the black hole. Look at it like this. Schwarzchild gets a solution. His sphere, right, the spherical entity that he has its center on the origin of coordinates, right? Now, that's what you expect. You've got a sphere with a center in it, like a football, like a soccer ball, for instance. It's got a center. And you've got the origin of coordinates on the center of the soccer ball. Now, let's take that soccer ball and we'll move the soccer ball away. It takes its center with it. But the origin of your coordinate system is still there. You've got your coordinate system there, but you've moved your soccer ball away from there so that the center of your soccer ball is no longer seated on your origin of coordinates. But your origin of coordinates is still your reference point for everything, because you've moved it away, you know what you're moving it from, right? Now, so it's the same with the Schwarzchild solution. Take that solution and move it away, right? like the soccer ball. Now, Schwarzschild's center of symmetry is now what is thought to be the event horizon, because they still think they've got a sphere with its center sitting on the origin, when it's not. There's no such thing even existing. So in other words, you can think of another sphere centered at the origin, drawn through the center of the sphere you just moved away, the soccer ball that you just moved away. But that's not a real object, right? So you've taken the soccer ball away, takes its center with it. They don't know what they've done, so they get these two singularities. So they think, oh, what's this singularity? Because they're thinking all the time that the origin of coordinates is still the center of spherical symmetry of the object, where it isn't. So now they come to the singularity of the so-called event horizon. That's the center of your soccer ball that we just moved away, effectively Schwarzschild solution, right? So
But
they
isn't
think,
the black
well,
hole still at the center of the soccer ball by
there
their
is no
model?
black hole. Schwarzschild solution doesn't have a black hole.
Okay, can
There
you
is no
elaborate
black
on that? Help me understand that.
Yeah, Schwarzschild solution does not contain a black hole. There is no black hole associated with Schwarzschild solution. Right? That was because David Hilbert modified it analytically and didn't realize what the geometry was behind it. So when he modified it, he changed Schwarzschild solution by moving Schwarzschild solution, his spherical object, away from the origin of coordinates. So the center has now gone with it. Now, the origin of coordinates is still there, but that's not the center of symmetry anymore of Schwarzschild's object. And Hilbert thinks that the center of symmetry of the center of spherical symmetry is still at the origin, but it isn't. It's somewhere else. So he's perplexed. Everybody's perplexed. How do you get these two singularities now? Well, that's because the center of symmetry is actually what they call the event horizon. And then they think there's something below the event horizon. No, because now you're moving down to the origin of coordinates where the center is no longer located. So in other words, when you move something, you take the center with you, but you don't take the origin of coordinates necessarily with you. You've taken the center of the soccer ball with you. So think again. You've got a soccer ball. Its center is on the origin of coordinates of your system. Now move the soccer ball away. Takes its center with it. That center is now no longer sitting on the origin. What happens if you don't know that it's been moved, and now you've got in your equations these 2 points that look funny? One looks like it's a center where you so-called get a division by zero in your mathematics. And now you've got two of them that produces division by zero. Well, the first one is where the center of symmetry is now really located because you moved it away. And they don't know that. They think the center of symmetry is still down at the origin. So they want to find a way to construct a mathematical expression that will give them a way to drive the center of symmetry to the origin where it's not actually the center of symmetry. And so they commit a violation of geometry. That's assuming, of course, that these mathematical expressions from Schwarzschild and Einstein's theory have any meaning. So in other words, the black hole itself is due to a violation of geometry and is not due actually to general relativity, but it's assigned to general relativity because they haven't realized this geometric blunder. Right?
So all the relativists, you can keep your relativity for the moment, but the black holes have to go.
The black holes, yeah, they're nonsense. Now we come to relativity. Let's get back to relativity.
Hold on. I want to understand the reasonable interpretation of Schwarzschild's equation.
The reasonable interpretation is this, that he has a spherically symmetric solution in a space that contains no matter, right? And the point at which the center is located, well, that means you've got zero volume there, right? That does not produce two singularities in his solution. In other words, there's only one singularity in his solution, and that is the center of symmetry, right? And by moving it away, as Hilbert did, the center of symmetry of Schwarzschild's solution becomes their event horizon. And the origin of coordinates, which is not the center of anything, right, just the origin of coordinates, they've assigned as the center of symmetry when it isn't.
What's the significance of... What's this? Schwarzchild's solution have been significant without Hilbert?
I'm sorry, what was that question again?
What's the significance of Schwarzchild's solution in and of itself without Hilbert having modified it? Would it have become meaningful in astrophysics without Hilbert having made black holes?
I would suppose that we wouldn't have black holes if they realised what the problem was, but they still have some nonsense, because that assumes, of course, that Einstein's special of general theory of relativity is actually meaningful, but that isn't the case, right? We've seen that it has no basis in cosmological reality. For instance, the cosmic microwave background, it doesn't exist. The so-called black body spectrum associated with that doesn't exist. In the late 1980s, Professor Haruni, using the most sophisticated or most sensitive radio telescope ever built during the Soviet era in Armenia, took a sample of the universe and found that there is a zero, returns zero for the so-called cosmic microwave background. The reason is this: Haruni's antenna is a very ingenious design, right? The dish in which the detector is located is hemispheric, right? It's not parabolic. And so you don't get any diffraction from the surroundings getting bounced around inside the dish and into the detector. Haruni called it effectively an antenna without edges for that reason, right? And the self-noise of that antenna was 2.6 Kelvin. Well, that's about the temperature of the alleged cosmic microwave background. So when Haruni took a sample of the cosmos to see if there's this cosmic microwave background present, the antenna returned 2.6 Kelvin. Well, that's the self-noise of the antenna. In other words, there was nothing contributed from the cosmos. There is no cos-CMB. And this is the most sophisticated, or most sensitive, rather, radio telescope ever built. It's now out of commission because with the collapse of the Soviet Union, the funding of that telescope dried up. So it sits there in limbo in Armenia, neglected. But here's an interesting thing. When I found out about Haruni's telescope, I made some inquiries about it, and I found that Haruni's paper, which was published in a journal in Greece, a small journal, had been removed from the journal's archive. So this is very strange. So I went to Armenian scientists who had the original journal on their laboratory shelves, right? So I got them to send me a copy of Haruni's paper with the journal details. Then I took a copy of that and I went to the journal editor. I said, well, where is this paper? He said, I'd never heard of it. He was a new journal editor. They got the old journal editor. He said, yes, it was published. And I said, well, why is it in your journal? It's not in your archives. All mention of it has been scrubbed. It's been removed. He tried to tell me, he actually wrote in an email to me that, we've discovered that it was an administration error, a clerical error. No, it wasn't. How do you have a clerical error? Write all record from your journal in all your electronic archives that this paper never even existed. But I've got a copy of it from the Armenian scientists from their laboratory shelves proving its existence. They reinstated it, right? And they put the journal, they put the paper not where it should be. So even if you go to their archive, you can't find where the journal, where the article is supposed to be listed because they stuck it in as an appendix on a different issue in their archive. Well, this is skullduggery, isn't it? Hiding a paper, removing it, and only trying to claim that it was a clerical error when I came along with a copy of the paper, as I've explained. It shows you what's going on in science. Now, here's another example of this kind of thing, so-called peer-reviewed science. It's rubbish. This is peer-reviewed, and they didn't like it in the end, the cosmologists, so what are they doing? Removing papers from it as though they didn't exist. Well, I managed to have that one reinstated because I carried out an investigation, if you like, into it and got it back. But it shows you what's going on in science. Now, let's take the Hafley-Keating experiment. the so-called experiment where they put cesium clocks in 2 aircraft and fly them around the world, and they compare the clocks and say, well, this is a demonstration that the theory of special relativity is correct, right? Well, the inventor of the cesium clock, cesium atomic clock, right, was Louis Essen. Louis Essen was an Englishman, right? He was personally known to Mr. Ivor Catt. I know Mr. Ivor Catt. I visited him in the UK when I visited there, and I stayed at his home. We had interesting discussions on various parts of science. And he has as an A-side, he has a box there of documents that belong to Oliver Heaviside. So I got to read Oliver Heaviside's actual letters and documents. There's a couple of boxes of them. And I even got an old tie of Oliver Heaviside. It's in the box, one of his old ties. It's fallen to bits now because it's pretty old. So because Heaviside died in 1925. Right? And he fell from a ladder. And that's how he died. He was about 75 or so. He fell from a ladder and landed flat on his back from about an 8-foot fall. And I read the letter that he wrote to a mathematician describing how he had this accident. Anyway, I won't go to that. It's interesting, but it's not relevant to the point that I'm making. Here is this. Louis Essen is the inventor of the cesium atomic clock that Hafley and Keating used in their experiment. And he read their paper and he said, my clocks can't do that. I invented them. I know they can't do that, but they've said that they've used them for and how they made them work. He says it's impossible. So he wrote
why is that? What did he mean by that?
Yeah, what do you mean they can't do that?
Well, they can't get the accuracy that they claimed that they got with these clocks. It's not possible, right? And Essen knew that. So Hafley and Keating had published it in Nature. So Essen wrote an article and sent it to Nature explaining why the Hafley-Keating experiment is meaningless. It's rubbish. Nature refused to publish his paper. Outright. Refused to publish his paper. He wrote an article about how Nature refused to publish his paper. And he managed to publish that in a very small journal. It might have been the Hadronic Journal. Can't remember exactly, and you can read it. I've got a copy of it, as a matter of fact, myself. So Essen says, well, this is what happened. I wrote to Nature. They refused to publish it, and they didn't give a reason. Why? Here's the inventor of the cesium atomic clock telling you that this Hafley-Keating experiment is nonsensical. It can't be done the way they've said they've done it. The accuracy of the clock can't do it. And so their claims are false. Essen was a fused publication, so-called peer review at work. Right? And in the article that he wrote about how Nature, the journal of the editors of Nature's misconduct, he wrote an article about it and explained that as well. And in there, he quoted Soddy. You might recall Soddy was a British scientist who worked with Rutherford. Yeah? Soddy said, in his view, right, that the theory of relativity is a swindle. And Essen quoted that in his article, explaining what happened with Nature, how they refused to publish his article, explaining why the Hafley-Keating experiment is just baloney. Now, again, we see another example of peer review at work. Blocking papers, removing papers. You know, I've got that one removing paper of Professor Harouni. Why do they want that removed? Because his radio telescope noise is 2.6. He returns on a sample of the universe 2.6. What's the CMB contribution? 0 Kelvin. And that's what Harouni wrote in his paper. 0 Kelvin. There is no CMB. Well, the cosmologists don't like that. So, and unfortunately, the Armenian telescope just sits there. It's still in order, but it needs to be upgraded, of course, to modern technology with computers and such. But there's no money to get it operational again. So his niece, Professor Aravik, I forget her surname, his niece, she trained under Harouni, and she has been trying for years to get the Armenian government to supply some money to recommission the Harouni telescope. It's still the most sensitive radio telescope in the world. It's just out of commission. right?
Yeah, we actually met with her on the phone, or we met with her over Zoom a couple of times. We were hoping to do a podcast, but her English wasn't,
No.
I don't think she was comfortable enough speaking. And
Yeah.
but that's one of our long-lived dreams, is to be able to go and make a documentary at the actual telescope and tell this story a little bit. I think we'll eventually get to it down the road.
Yes, yes. So here you have a direct measurement is also telling you that it's not there. And the analysis by Dr. Robitaille of the Covey-Furis and the WMAP and the Planck satellites prove that they haven't got any signal at L2. There is no CMB being sampled at L2, so-called cosmic microwave monopole signal, not at L2. The WMAP was a differential instrument, so it couldn't even determine if there was one at L2, even though it was at L2. So the only one you've got is Covey-Furis at 950 kilometres or so above Earth. Well, that's because the Earth's a signal, as Dr. Robitaille has pointed out, because the mechanism that it produces the emissions is the hydrogen bond in water. Everybody knows that if you put a glass of water in a microwave oven and turn it on, what happens to the water? It gets hot. Why? Because it's absorbing microwaves. Well, you know what? We know from the laboratory that anything that's a good absorber is also a good emitter, and including an emitter at the same frequencies. So that means water has the capacity to emit microwaves. Right? So
there's another smoking gun that's worth mentioning too, that Pierre published recently in one of his videos, which is he discovered that communication satellites calibrate to the CMB when they're in, they align themselves based on pointing at the CMB. And where do they point their horns to align to the CMB? You would think, well, they just pointed at outer space, right? Because it's everywhere. That's where it's coming from. It's cosmic, right? But no, they point at the edge, the limb of the Earth, right at the far edge.
Right at the limb of Earth.
And you're like, so why? And you ask, you go into that paper and say, why did they do that? And they say, that's where it's most apparent.
Yeah, it's because it's coming from the Earth. Anyway, the details of that are also in Dr. Robitaille's paper, where it's available free online, where he analyzes he calls it COBE, a radiological analysis. There's another one, WMAP, a radiological analysis. Anybody who's interested in that can go and read that, and you can see all the fallacies that are involved in these satellites. And the Planck satellite as well, he's analysed that one as well. The Planck team is a joke. You know, they take their black body, they have a onboard black body on the low-frequency instrument, the LFI, right? Which they use to say, oh, well, we'll sample the CMB. But they didn't sample the cosmic microwave monopole signal at all. And their black bodies, they connected to the cooling system, right? Well, now you've got a conduction path from the so-called black bodies to their refrigeration system. I call it the refrigerator, right? Just to be a bit facetious with these clowns. So now you haven't got a black body because you've got conduction from your so-called black body to your heat sink. It's a heat sink, right? And they were so silly, they even wrote in their paper how they use these wonderful thermal washers and screws to make it connected up, not realising that now you haven't got a black body anymore. You know? So they didn't have even a black body comparator on board. It's a joke. The Planck satellite's a joke. You know? But so it didn't sample any cosmic microwave background there either. So you see all of these things relate back to what? Kirchoff's law, temperature, thermodynamics. This is why it's so important. You know? And so
there's been some really interesting attacks on the WMAP data lately. I don't know if you've been following this, but I came across some interesting issues with regard to the Doppler shift. Like there's a particular isotropy with regard to the direction of the motion of our galaxy with respect to the CMB. In other words, it looks warmer depending on the direction of the motion of certain bodies, including our solar system, but also the galaxy itself. And this has actually been the most mainstream attack on the whole operation that I've seen in recent times.
Well, Dr. Robitaille revealed all of this long before this sort of thing came up. So the definitive works are his, and anybody who's really interested in the facts can go there. And you can see he's an expert in imaging science as well as being an expert spectroscopist, a physical chemist. He's an expert in imaging science because he's the inventor of ultra-high field MRI. So he knows a lot about imaging, more than those guys do with their satellites looking at stars, right? And if you had the quality of their imaging in medicine, you'd be laughed out the door, right? So he knows.
And he's such a careful and kind scientist. I think that's the reason I love Pierre so much. Is he takes so much abuse from people, and he just has this ability to realize that they're suffering from their human conditions, their careers, and all of these things, and not to get angry at them. He has this way of just realizing that this is what must happen, and people will eventually understand that I'm right about these things. But he doesn't have the bitterness that you often associate. And I think that's, God, that's just charitable. Supernatural almost, his ability to stay centered in the midst of such horrendous vitriolic attacks.
Yes. He's perhaps more charitable than myself, but I'm not angry either. I couldn't care less. I'm just going out there and telling the truth. They call me all sorts of things too, but it doesn't ruffle my feathers. I couldn't care less. So it doesn't make me angry, doesn't make me anxious. I just have a laugh, go along, and they scream and yell and carry. Even my current video, and I have another video lecture with on a Dr. Advertised channel where I'm dealing with special relativity, and if you go and see the comments there from these relativists, it's laughable. And I don't know what's in their mind. Do they think that they make me upset with their comments? It doesn't bother me. For me, it's a hobby, because I'm not going to waste my life on this kind of nonsense as something that's a central issue in my life. They have it as a central issue in their life, and I see what it really is. It's nonsense. And it's not difficult to explain, and I do it in my spare time, and I don't have much spare time. I've got lots of other things that I want to do. My life's more important. To me, there are more important things in my life than just wasting my time with these nonsensical calculations and such. But, I go out there and tell the truth about it, and they call me all sorts of things. Look, I've got one from the University of Adelaide. I got, for instance, a scientist there. He wrote an email to me and called me a poo-brain dick-ass. Then he wrote another one later. Yeah, I'm not kidding you. From his email account, so I have the copies of them. So it's all evidence. And then he called me a C. You know what a C is, don't you? In another email. And then he called me scum in a third email. And those three emails came within 1 minute of each other. That's in 3 minutes. So I sent it to the University of. I said, "This is a laugh." I laughed at it. I thought, this is ridiculous. This guy's. What is he? Is he 5 years old? Anyway, I sent it to the vice chancellor and the head of school at the physics department at the University of Adelaide, and they ignored me. They ignored the complaint. Can you believe it? Even though I gave them the emails, I said, "Look at this. What's going on here?" Then I said, "Okay, I'll have a bit of fun with this." So I sent it to the newspapers. Yeah, well, the newspapers took it up. The Adelaide Advertiser took it up, made a big story of it. It was mirrored in the Courier in Queensland, up in Brisbane way. It's a lot, thousands of kilometres away. So it got a lot of play in the media. Only then, when the journalists contacted the university, did they decide to say something. And what do they tell the media? You can read it. They said to the media, "Oh, well, we encourage academic debate." No, you don't. That was a blatant lie, because they said nothing when I complained about this guy. I just sent it there to see what would happen. Because I had a death threat once from a guy at the Max Planck Institute. I'm not telling you a lie. Yeah. So I sent that to the Max Planck Institute and to the Max Planck Society. They ignored it. They let him get away with a death threat. Unbelievable. So this is what you might call peer-reviewed science, the methods of peer-reviewed science. Yeah. But I've been around a long time. I'm not a young bloke, and I've got a lot of experience in forensic investigations. I've dealt with some ugly customers in my life. I don't care about cosmologists. It's a waste of time, So, but I'm not going to let them get away with this nonsense. It's so easy to prove that it's rubbish, right? But the problem is they're leading many people in their early careers up a garden path and then causing them to waste their lives on meaningless investigations.
That's the saddest part, I think.
Yeah, see.
I mean, the first thing I tell all of my students is when you see the word dark or black or any of these death cult words, it basically can resolve to, we don't understand this phenomena. And I'm like, look, kids, that's the cool stuff that you need to understand, because what you're hearing when you see that label is that those are the holes in our understanding. Those are the phenomena that we don't understand. Those are where the fresh development can come from. If you move past thinking that you're too dumb to understand the mathematics or something like that. Those are clearly aspects of these giant theoretical landscapes that are not understood. And when you start looking at it that way, it really becomes a much more inspirational field, because there's a lot of work to be done.
Yes, there's plenty of things to discover. But if you're sidetracked on things that you end up making a career of and it's rubbish, you've now taken away that person's career aspirations, really. You've taken away something they could have done better with their lives. Right? Just because you've now wasted your life on nonsense, do you want to now be spiteful and do it to someone else and keep this going? Well, what is this? So I don't, but I don't have an academic post. I don't want an academic post. I don't want to rub shoulders with those academics because they're so stupid. And yet they think they're such geniuses, And they don't like me because I'm brusque, I'm not couth. I think that's uncouth, isn't it? You're not couth?
I got super lucky when I was absolutely shocked that I even got an interview for teaching astrophysics and cosmology, because I show up to the interview and the department chair is telling me, about the curriculum. And at some point she mentions that the second semester involves talking about black holes. She's like, we're going to do all the black holes and the Big Bang and all this crazy stuff. And I kind of clammed up, right? I didn't know what to do, because since I was 11 years old, I wasn't buying any of this stuff. And she saw that I was clamming up, and she's like, or you can talk about how maybe those things didn't happen at all. And I was like, really? And she's like, yeah, I mean, the James Webb data is pretty strange, and you should explore the topics. And I was like, wow, this is crazy. And I think the only reason I can get away with this is because I'm not at a research institution. There's no astronomy department to tell me what to do and what not to talk about. And so it's a pretty strange and awesome situation that I have, that I don't think most universities are privileged to, because the research and the money is all tied up in the narratives that are taught to the undergrads. So
of course.
It can happen, is all I'm saying. It is possible.
The next one I want to talk about is the LIGO. The LIGO-Virgo detection of gravitational waves, right?
Mm.
Now, did they detect gravitational waves? Well, first, of course they didn't detect gravitational waves. That's on the assumption that they even exist. And where do they get them from? Colliding black holes, or colliding black holes with a black hole with a neutron star. Well, black holes don't exist, so they certainly didn't get gravitational waves from black holes. And Einstein's gravitational waves don't even exist. So what I want to do is show you how the LIGO team gets their gravitational waves. It's another piece of magic, or it's deception. It's deception combined with mysticism.
Extremely wishful thinking, perhaps?
Oh, even more than that. It's actual deception, and I'll explain to you why. And I've got the facts, so I'll show you documents. Here we are, to show you that, yes, that's what they did. Then I can name names because they come from their university accounts, which I will do for the fun of it. Okay. So some interesting. And I've got a little joke. It's not really. It's a funny thing, and I'll tell you about. After I've done that LIGO bit, there's another thing I want to tell you about. Anyhow, so righto, LIGO says that what was it in 2016? 2016, they say that they got this first detection of gravitational waves, and they used the LIGO and the Virgo collaboration. Virgo's in Germany, and the LIGO, of course, are in the United States. And they say, well, look, they had two colliding black holes. They don't tell you what type of black holes. There's 4 types, right? You got Schwarzchild black holes, you got Reisner and Nordstrom black holes, you got Kerr black holes, and you got Kerr-Newman black holes. They don't tell you what type of black holes they allege, And how did they get 2 black holes when Einstein's theory, you can't even write a set of equations. You can't even write a set of equations for 2 bodies. Give me a set of equations for 2 bodies before you start talking about 2 black holes. In Newton's theory, you have a two-body problem, yeah, you can solve that. A three-body problem, no, you can't solve that. But is there any limitation perceptually or theoretically in Newton's theory? No, you can put as many masses as you like into this universe. It doesn't stop you. Right? Now, in Einstein's theory, you have to have a set of field equations for every configuration of matter that you want to propose. So if you want two black holes, well, they're big. They're both big black holes. So one's not minuscule and one's not really big. So you can give what they call a perturbation. Right? You got two big black holes. Well, you better give me a set of field equations that describe your two black holes, and you better solve them to give me a solution for their interaction. And if you can't do that, give me the existence theorem that shows you that you can, that at least this configuration exists within the theory. They can't even do that. Right? So where do they get the two black holes? They superpose them all and stick them all inside a Big Bang universe using a theory that's nonlinear. That means you can't superpose, but they superpose everything. So you can't do that. It's like a set of differential equations, right? You have nonlinear differential equations. In ordinary differential equations, for instance, you have a solution and you have another solution. You can add those two solutions together and you've got another solution to the differential equation, right? But in a nonlinear system of differential equations, you have one solution and then you've got another solution. You can't combine those two solutions to get a solution because it's nonlinear. Einstein's theory is a system of nonlinear differential equations, partial differential equations, in fact. So in other words, if you want to talk about two bodies, write a set of field equations and solve them for two. Or if you can't do that, at least give me an existence theorem to prove that there are ways, there are such equations, but you don't know how to write them. But you've got an existence theorem, like in mathematics, there are existence theorems. You might not know how to get one, but you can prove that they're out there somewhere, right? Well, I haven't got that either. So how do they do it? They superpose everything. And a black hole set of field equations is completely different to their Big Bang equations. So now they take the Big Bang and they stick just pile them all up as though they're doing Newton's theory. It's complete rubbish. Anyway, we get back now to LIGO because that's a basic idea of how they do this shifty stuff. I call it le jeu de main, it's linguistic le jeu de main, or sometimes it might be geometrical le jeu de main. Either way, it's sleight of hand, right? So we come now to LIGO. In 2016, they say that they've got this two black holes combined. One's 29 solar masses, one's 36 solar masses. And then they combine. They don't tell you what the types they are, remember? And then they combine, they crash into one another, even though they're superposed. And they make one black hole, producing a curved black hole. Well, that's got rotation, right? So rotating, it's got angular momentum. So, and then three of the solar masses get evaporated, if you like, and turned into gravitational wave energy and radiate away as gravitational waves. And that's the waves that they say that they detected with the LIGO-Virgo contraptions. Right? But I'm going to tell you now how they did it. First, if you have an instrument, you have to calibrate it. Isn't that right? You know that, right? You've got to calibrate it. Well, Dr. Wolfgang Engelhardt retired from the Max Planck Institute. He's now deceased. But I knew Wolfgang Engelhardt. I visited him in Germany. He was in Munich. And we had discussions. But I also visited him before that, some years before that, in Salzburg, when I was traveling, seeing scientists and others. Now, Engelhardt was as I said, he spent most of his career at the Max Planck Institute. And he discovered that the LIGO collaboration has never published a calibration curve for their machine, right? And he approached Professor Carsten Dansman. This is all, mind you, on a website that's still there, even though Dr. Engelhardt is now deceased. The website is still there. Anybody can go and read it, although much of it is in German. Quite a bit of it's still in English. Now, Dansman, he prevaricated all the time for months and months because he couldn't produce a calibration curve. In the end, when he was threatened with legal action under German law to provide this information, he came clean and said, well, they didn't really have one. Well, you haven't got a calibration curve. In other words, they must produce a calibration curve for a measured displacement of their mirrors for a known laser input in the attometer range, right? Attometer range. They haven't got a curve. They've never produced a curve. To this date, they have not got a curve. They've never published a curve. So they don't have a calibration curve, and the reason is they can't measure it. You can't measure it, and yet they claim that they have measured it. Well, where's your calibration curve? Engelhardt discovered they haven't got one, right? So that's
they
deception.
Can't measure it. Why do you say that they can't measure it? Just because it's down to such significant figures
exactly.
that it's impossible?
You cannot measure it in the attometer range. And that's why they haven't published a calibration curve, because they can't measure one. And yet, in their discovery paper, what do they say? They say that they calibrated their contraption using their lasers. Well, that's a blatant lie. You haven't got a curve. Where is it? Darnsman couldn't produce it, and he never did. Now, that's on Engelhardt's webpage. So I take it from there and my discussions with Dr. Engelhardt when he was alive. Right? Now, I've got information that Engelhardt didn't get and no one else has got, because I did another investigation on it at the time. Because I read their paper and I thought, this is just, what do these terms mean? They've got all these terms. What do you mean by this? So I wrote to the Virgo collaboration. They were all drunk with the discovery, you know, that we've got these gravitational waves, so they were drunk on their arrogance. So I wrote them a letter, and I wrote it to the Virgo team, and I got a reply from Massimiliano Razzano at the University of Pisa. And these are his emails. I've kept them as evidence, of course. And this was on the 1st of March 2016. Because I asked him a few questions. My first email, what did I write to him? This was on the 26th of February, right? That was when I first wrote them. And I wrote to him and I said, well, you know, let me think, what date was that? Yeah, 26th of February. He replied to me the same day, you see. I asked him, I said, well, you've got these here, please clarify the meaning of this report, because I gave a quote from the paper. Our readers to take it that within the first 3 minutes of advanced LIGO looking for a gravitational wave signal, that it detected a signal matching GW150914. That's their code name for their detection. In the numerically determined database. So that was a bait, right? So I sent it to him and he says, he writes back to me, he says, thanks for your interesting question. And he goes on with a lot of rubbish there, but he talks about how they use this database. So I wrote back and I said, that's interesting. So I said, this is my letter on the 29th of February 2016, in reply to his reply. Dear Mr. Massimiliano Razzano, okay? He says, I said, thanks for answering my questions. I have a few more. How many numerically determined waveforms are in the database? They never publish this information, you see. And they call them templates, right? I'll tell you what templates are shortly. He writes back, 250,000 templates. 250,000 templates, right? I'll tell you what the template is. A template, a LIGO template is this. It's a fake curve. They generate, using their computers, fake curves using this general relativity with nonsensical equations for two or more bodies, right, which they haven't got proper equations for. They just make it up. And they have 250,000 different scenarios, right? We'll make this one a black hole and that one a neutron star. This one a black hole of this size and that one a black hole of that size, right? And we'll have energy for this. So they've got a whole bunch of hypothetical scenarios made up from their own stupid equations, generated by their own computers. And they call these fake curves templates. but they're just fake curves. That's a code name for fake. So they got 250,000 of them in that at that time, right? And they never published this. They've never published how many templates they've got. Can you imagine how many templates they've got now? I say that it's only constrained by two things: computer memory and the stamina of their computer programmers. You can generate as many as you like, and that's what they do. But then they had 250,000. They told nobody. I've got it. 250,000 fake curves. So what they did was they get a noise in the contraption. They call it a generic noise because they don't know what it is. It's some generic noise. They take the generic noise to their computer and they tell their computer, go and search the template database, the fake curve database, and find one of best fit. Well, you'll always find one of best fit, won't you? So they find one of best fit. Then they look at it and say, oh, what did we make there? Well, we made a black hole of this size and a black hole of that size and gravitational waves of this much. Oh, well, that must be what we detected. 1.3 billion kilometres away. Oh, no, 1.3 billion light years away, not kilometres, light years away. They never got out of their computer. And they're telling the world that they detected something 1.3 billion light years away when from fake curves of their own, 250,000 of them. All right?
Okay, so hold on 1 second. The idea that you would have a database of templates to which you match an observed event at your detector doesn't seem totally unreasonable to me.
Well, it's a generic noise. They don't know where that noise came from. It could have came from a truck 20 miles away.
Well, they detected it on different sides of the Earth, right?
So they say, but Engelhardt's analysed that too. And if you read his paper, it's impossible. The time difference between it's impossible. So people can go and read Engelhardt's webpage for that, right? I
have maybe a more fundamental question, which deserves to be asked at the beginning of this discussion, which is, why do you assert that gravitational waves are impossible? Like, let's say that it's not two black holes. Let's say that it's two suns, and so there's an object. There's a pair of bodies at the center of this system that are doing something massive. Why is it impossible, theoretically, for us to be able to detect that kind of perturbation when it arrives at Earth?
Because also, let's be fair, Heavisides and I believe Poincaré and others predicted these before any of this business in the modern day.
And if you,
that's true. They tried to do these things.
So we have kind of a filamentary understanding of the universe, which is that there are...
Let's just say interconnected, maybe.
Interconnected. Okay, so let's assume that the universe is interconnected, and when something happens really far away, there is some kind of tension-based network, kind of like a spider web, through which that perturbation can propagate. It seems possible, theoretically, that a big enough event that shakes that web hard enough could be felt at Earth. Whether or not the
detection has actually happened or not, right?
Yeah. So setting aside detection, I'm curious why you think that it's theoretically impossible.
Well, there are the two things. First, we know that they couldn't have detected because they haven't got their calibration curve. If you've got an uncalibrated instrument, it's worthless. Right?
Sure.
And we know that that's the truth. So that means their claim of detecting waves is nonsense. So now we ask the question. You've got now a whole bunch of curves that are generated by a theory that you just made up. That's a made up theory. These are made up curves. They're not curves that relate to anything, right? They're just made up. And you've got a noise in your machine, and you compare the noise to something in your database, and you picked one out. You didn't detect anything. All you've got is a noise in the machine. It could have been you don't know what it is. But because you've taken that noise and you've got a curve of best fit out of your database, you'll always get a curve of best fit. Right?
It's essentially a filtering issue. I like to use the example that, I love playing with synthesizers, for instance, and I can turn on different kinds of noise on the synthesizer, and then if I take the filter knobs, which essentially select the frequency, and I put a high enough Q into it, that is, I amplify a particular frequency very tightly, I can pull any note that I want out of that noise. I can make it sing a perfect A sharp if I want it to. But it doesn't mean that the noise is an A sharp. It just means that I've selected for the one little piece of that huge signal where I can get the tone that I'm looking for.
That's a different question than the one that I'm asking. I will grant you that if you have a filter and you apply it to your data, if that's white noise, you can get whatever signal you want. 100% agreed, no issues there. I'm asking a deeper theoretical question because you said at the beginning that gravitational waves are absolutely impossible, and I want to know why you think that.
Einstein's gravitational waves. Now, the reason for that is I say that over and above the nonsense of LIGO saying that they've got one. Well, we can see that that's not true. So the reason why I say Einstein's gravitational waves don't exist is there are two reasons. First, they say that they travel at the speed of light, and they get this from a calculation using the linearized form of Einstein's field equations. However, I delivered a lecture, or not a lecture, I gave a poster when I went to an APS meeting some years ago in Columbus, Ohio. I gave one lecture and I had a poster. And the poster, since I was only allowed one lecture, I had a poster where I dealt with this issue because it's mathematical, right? You linearize field equations and they get a wave equation from it, right? And they say, well, this wave equation shows that the waves travel at the speed of light. Well, that's not true, because when you analyze this, you find that the reason why they come out with this wave equation with the speed of light is because they selected a set of coordinates that gives the speed of light. In other words, it's what you call a vicious circle, or assuming as a premise that which you wish to prove, the so-called petitio principii. Because if you change the coordinates, you get a speed of propagation that's completely different to the speed of light. And I gave the mathematical analysis of that on the poster. I've written an article on this. I wrote an article on the LIGO nonsense, and I covered all the theoretical issues as well in an article that I published, that was published by the Hadronic Journal. That's a small journal, but they asked me if I would publish it there, so I did. So, of course, it wasn't going to ever be published in the mainstream journal. They just claimed that they detected gravitational waves. They weren't going to publish one that says they didn't. So anyhow, I show in there the mathematical analysis in detail how it is you get a wave equation travel with a propagation speed of c because you actually select a set of coordinates beforehand to make it come out to c. If you change the coordinates, you get a different propagation speed. So that means it's arbitrary, the speed of these propagations. Right? So you've chosen one because you want to make it match that you want it to travel at the speed of light, which is what Einstein's theory wants.
Do you follow why changing the coordinates changes the speed?
You won't be able to follow it without looking at the mathematics, a mathematical issue, right? Because it's a wave equation.
Yeah, it makes sense to me.
Yeah, it's a wave equation. How do you derive your wave equation? You start off with Einstein's theory, you linearize the field equations, then you get a certain thing, a certain mathematical complication comes out, and you can chop off a piece of it, and you end up with a selection of coordinates by doing that. And that's what they do. That's
and
what
to be fair, Einstein recognized this, and he also didn't buy the gravitational wave stuff either, from what I understand. I know other people promoted it, but Einstein himself didn't think that his mathematics were capable of supporting the idea.
Okay.
You can fact check me on that. Somebody tell me if I'm wrong, but last time I looked
if
into
he said that, I'm not aware of it. But if he said that, then he's correct, because it's coordinate dependent. Even Eddington knew that. Even Eddington knew that. You can read his book in 1923, The Mathematical Theory of Relativity. Eddington even discusses it there.
It might have been one of those things where Einstein came around to it later or something, but I know that he wasn't a fan of the idea in the initial form.
Yeah. Now, it goes even further than that, though, because when Einstein published his paper, his theory of relativity, general relativity, in 1915, he presented it in what he called, or what are called, unimodular coordinates. And this is because he set a condition that the square root of the negative of the determinant of the metric tensor is equal to 1. Okay, now we're talking mathematics. It gets complicated, and that's what we want to really avoid for the general audience, right? But that's a technical thing. He's got unimodular coordinates in his 1915 paper. That's where he introduces his pseudo-tensor in the same paper. And his pseudo-tensor acts like a tensor under linear transformations of coordinates, right? Now we're getting more complicated. But since it acts like a tensor under linear transformations of coordinates, you can contract it. And when you contract it, you get what's called a linear invariant.
I have a really basic question. What does it mean to do a linear transformation of coordinates?
That means, well, you got, linear means power of 1, right? Your y equals x, that's a linear equation. So if you transform the coordinates from x prime equals x plus some constant, now you've got a linear transformation from x to x prime, right? So it's a linear transformation, okay? So only under those linear transformations of coordinates does his pseudo-tensor act like a tensor, right? If it's not under linear transformations, it's a pseudo-tensor. It doesn't act like a tensor, but it does under linear transformations. So you can contract it like a tensor. You get a linear invariant. It's linear because it's under linear transformations, right? But as Levi-Civita pointed out in 1917, he wrote a paper on this himself. And Levi-Civita, Tullio Levi-Civita, and Giorgio Ricci Cabastro in 1901, they're pure mathematicians. They're inventors of the tensor calculus. They proved in 1901 that it is impossible to construct first-order intrinsic differential invariance. What does that mean? It means that it's impossible to construct an invariant solely from the components of the metric tensor and their first derivatives. That's why it's called first order, right? First order. Impossible to construct first order intrinsic differential invariance, right? That's a theorem. And as I said, they were the inventors, principal inventors of the tensor calculus. Now, Einstein proposes a pseudo-tensor acts like a tensor under linear transformation. You contract it and you get a linear invariant. It's a first order intrinsic differential invariant. They just proved in 1901 you can't do that. So that means Einstein's expression, if you assume it's true, you get bunkum, a falsehood. So that's the method of reductio ad absurdum invented by the Greeks. For example, the proof that square root of 2 is not rational. You assume it's true, then you show that it can't be true. Therefore, your assumption is false, right? So because you assume it, then you show something that can't be true. You know it's not true by logical analysis. So you say, okay, that means our assumption is false. That's called reductio ad absurdum, reduction to absurdity. So now let's assume that Einstein's pseudo-tensor acts like a tensor under linear transformation. Yeah, well, acts like we can contract it. We get this in differential invariant, but you can't. That means his unimodular coordinate system of equations is false. The reason is you can write Einstein's original field equations in unimodular coordinates explicitly in terms of his pseudo-tensor. And the pseudo-tensor that allegedly describes the energy and momentum of his gravitational field. And it's used, the pseudo-tensor, to calculate the energy of his gravitational waves. But the pseudo-tensor is a meaningless concoction of mathematical symbols because it violates the rules of pure mathematics. And
so we get into a case where theories stacked on top of other theories,
which, as I said before at the start, stacked on stacked on stacked of nonsense. So now, that means you can write, as I said, Einstein's original field equations, the unimodular field equations, in his 1915 paper, you can write them explicitly and equivalently in terms of the pseudo-tensor, which is contained in that paper. Since those field equations are false, so are the others because they're equivalent. That means his 1915 paper is baloney. That means all the productions of gravitational waves from that theory are baloney. Notwithstanding that the fact is that they're coordinate dependent anyway, even if the theory was right, which it isn't. Now, there's another problem that, because of this problem, other physicists recognized that Einstein's pseudo-tensor had limitations because it was not symmetric and it did not count for angular momentum. So in 1948, the Russian physicists Landau and Lifshitz developed another pseudotensor, which they could try to formulate conservation of energy, for instance. This is needed for conservation of energy. That's why Einstein invented the pseudotensor, because he needed to add energy of the gravitational field to the energy and momentum of the gravitational field to the energy and momentum of his material sources of the gravitational field to get a total energy and momentum for a closed system which he can conserve, right? And with his pseudotensor, he says he gets a conservation law. Yeah, because a mathematical expression comes out and it looks like it. But the trouble is it's a nonsense expression. Okay, so Landau and Lifshitz come up with another pseudotensor. It also acts like a tensor, only under linear transformations of coordinates. It's much more complicated than Einstein's pseudotensor. I proved in a paper that if you contract this pseudotensor of Landau and Lifshitz, you get a first-order intrinsic differential invariant. It goes back again to 1901 when the pure mathematicians proved that you cannot construct such a thing. So that's bunkum. That means the Landau-Lifshitz pseudotensor is another meaningless concoction of mathematical symbols. It looks like mathematics. It's got all these mathematical symbols. It has the appearance of it, but it's actually mathematical gibberish because you cannot construct such an invariant from it. That means it's false. So now Einstein's theory of general relativity is false. You have no field equations, right, to even use. So what do you got? Zero. So you have no Einstein gravitational waves at all. That's why I say it's impossible to even generate or get gravitational waves from Einstein's theory, right? Because you can't linearize a nonsensical theory and get gravitational waves and then select a set of coordinates to make it true, to travel at the speed you want, when the whole theory itself is false. The pseudotensor can't be used for anything. They use the pseudotensors to calculate the energy of their gravitational waves. Great. Well, how do you get the energy of that when they're nonsense expressions? You can't. Right? Now that brings me to special relativity, because the general relativity is a generalization of special relativity. So it gets worse. In 1905, Einstein published his special theory of relativity in a paper called On the Electrodynamics of Moving Bodies. And I read this paper many times, and I found that the only real part that's of really importance is his alleged proof in section 3 of his paper. But there are some curious comments in sections 1 and 2 as well. And here is, I've got them here that I'll read them to you. And as I said, this is from On the Electrodynamics of Moving Bodies by Albert Einstein in 1905, published in Annalen der Physik. You can get this paper for free online in both German and in English translation. Now, remember, time and speed of light are very important for Einstein's theory. Time and clocks, he talks about clocks a lot, right? In section 1 of his paper, he says this: it is essential to have time defined by means of stationary clocks in the stationary system, and the time now being defined appropriate to the stationary system, we call it the time of the stationary system. What has he done here? He says he defines time by clocks. Clocks don't define time, they measure time. That's like saying I'll define what pressure is by using a pressure gauge. Pressure gauges don't define what pressure is. All measuring instruments are invented to measure something other than themselves. They don't define the thing that they're measuring, right? But Einstein's defining time by his clocks. Now in section 2, he goes further of the same paper. Time here denotes time of the stationary system and also position of hands of the moving clock situated at the place under discussion. So not only is time is time, and it's also the position of hands on a moving clock, because he's defined time by means of clocks. Time is not defined by clocks. Clocks measure time. In section 3 of his paper, he talks about moving systems.
I have a question.
Yes?
Do you have a definition for time?
No, I'm not going there. I'm just saying time is something that we measure. What is time? Well, what is gravity? You know?
Gravity is a lot easier. Gravity is clearly just atoms pulling on each other. Time seems to require complex ideas like memory, because you need to be able to compare the motion of something to some standard. It's a very complicated and
Yes.
abstract concept.
Yes.
It's not dependent on just one body with respect to another, a primary concept, whereas gravitation is pretty easy
Yeah.
by contrast.
Now,
Well,
but as I said, that would take
hold
us
on,
further afield than for the purpose of relativity.
I actually think it's pretty. If you just take Einstein as when he says time, he just means what the clock does. Everything makes a lot more sense.
Yeah, I'm like, is it invalid to say that time is what the clock does?
Of course, because clocks can tick and tock it any way you like. I can make two watches, and one of them doesn't run at the same rate as the other one. Which one's got time? I can take, if the clock stops, does time stop? Clocks do not define time.
No.
They only measure time.
No, but I think it's important to take him at his word, and this is the problem, right? Like, especially with the GPS experiments or any of these experiments that measure time dilation, if you just realize that all they're saying is they're measuring the clock being affected by gravity, it just becomes a lot more physical, right?
Of course.
Like you've pointed out before, if you take a pendulum clock into outer space, it stops working. And it's like,
yes.
Well, that's because the pendulum clock depends upon the pressure of gravitation. And so, of course, clocks are going to be affected by gravity. And it just becomes a lot less spooky. I just tend to take Einstein right at his word and be like, all right, he means clocks, the way they behave.
Yeah, and I guess that's what I'm trying to get at, where I'm just trying to make sure that that's a point that we can all agree on, that if you treat time as the thing that clocks do for the sake of the thought experiment, then you have to deal with the next question, which is, why is it that gravity affects what clocks do? And that's pretty straightforward. And so you can go from something that seems really weird and rationalize it in a relatively straightforward manner.
Well, I see what Einstein says. He says in other places, for instance, in his book with Infeld, he says that there are infinite number of spaces and they've all got their own time. And all these spaces are moving with respect to one another, and they've all got their own time, right? So he's talking about time, and he makes his clocks define time. Then he stops talking about time and talks about clocks, but he uses that as time. That's how he gets his twins paradox, right? And in time dilation, this is time that's different, not just the clocks. The clocks are actually measuring, because they're supposedly synchronized in their systems, they're actually measuring time, right? But so for him, when the clocks in motion are actually different, he's saying that time is different, right?
Yeah, I think so much headache would have been avoided if he'd used a different variable than t, if he had not called what clocks are doing time, if he could have just called it clock readout or something.
Right, because
I know that's complicated, but it would have been so much more honest and so much less woo would have been produced.
Okay, so I think that the rationalization of this that explains the twin paradox is that you make a mistake in thinking that the clock as it changes in its local area is reflexive of some kind of universal change. Right? Where if the clock is changing, that it's somehow changing with respect to a universal time. And so you're experiencing something different when you're in the vicinity of that changing clock and where you're under the same conditions as that changing clock. But time is, I think, a measurement of the relative motion of the entire universe, where it has been relative to where it's going. And so there is a clock that moves and it changes, but the rest of the universe doesn't necessarily change significantly by virtue of that clock's motion.
It seems like a classic map for territory mistake.
Yeah, exactly. And it's the overgeneralization thing as well.
Of course, exactly. It's the universalization business. I mean, I hate this word theory of everything so much with a passion, honestly.
Don't tell Kurt.
Yeah, I know, but if you try to explain everything, you end up explaining nothing is the problem. Of course. It was one of the first things I learned in doing my own research when I was back at the university was that you can't say everything in one paper, right? Otherwise, you run the risk of losing everyone. You have to focus on a tiny little piece of nature and explain that within the confines of the system. And I just have no stomach for people trying to explain everything all at once now, or trying to come up with fundamental explanations for things. It's like, that's just not science. That doesn't mean anything at some point.
Yes, I agree. Yes, I agree. So, would you like me now to talk about how the Event Horizon Telescope managed to make an image?
Mm.
Okay, I'll tell you how they did it. So the Event Horizon Telescope, okay, they have a thing called synthetic images. What they did was they, again, got their computers to make up some images as compared to the 250,000 templates of fake curves that the LIGO team made. They used 420 models, made up equations, right? Got their computers to generate over 62,000 fake images. They call them synthetic images. Very convenient name for fake images. And they put them in their synthetic image database. Well, let's tell it what it really is. It's a fake image database because you made them up. Then they, from a radio point source, they make something up with an algorithm in a computer. Then they go off and take that image that they generated with an algorithm from a radio point source, and they go and search their synthetic database of more than 62,000 fake images, right? And they find the one that's the one of best fit. Now, instead of doing what the LIGO team is said and take one out of the database, they didn't do that. What they did was they kept the image that they made in the computer, their generic image, and they used the parameters of best fit for the fake image that they made and assigned those parameters to the thing that they made in the computer. That's how they did it.
Seems like a trend appearing here.
Mm.
Yeah.
Definitely.
So LIGO has templates for fake curves. They call it templates, and these people call their fake images their fake images synthetics. Yeah. So that's how they did it. So did they actually detect something out there, image something out there? No, they didn't. They never got out of their computers, just like LIGO never got out of its computers. So they didn't detect a black hole or rather image a black hole in M87. Not only that, we've just established that, well, you just saw that black holes are so ridiculous, they don't exist. So they've managed to make an image of something that doesn't exist. A finite mass concentrated in zero volume with infinite density and infinite gravity with a speed of light as the escape speed from which light can't escape.
I imagine that our descendants will one day look upon this the same way we look upon the Sumerian astrology or something, where it just seems so foreign and absurd that they are forced to think of us as superstitious dum-dums, despite all of our... right, because the Sumerians were brilliant, right? And the Greeks too. Well, the early... let's say the Indian astronomers, but they had their religion really wrapped in with their science in a way that we look at now and we just think how primitive it was. But I would love to be a fly on the wall 1,000 years from now or whenever people actually straighten all this business out.
I think, I agree. Science has got to be straightened out because it's gone down a wrong path, and it's been going down a wrong path for a long time. And we can see that a number of particularly significant markers in history, 1859 with Kirchoff in his magic boxes, Einstein in 1905 with his magic clocks, 1915 with warp space-time and all the rest of it. Oh, I left out Mr. Minkowski in 1909 because it was he who invented the four-dimensional space-time continuum, not Einstein. Einstein adopted it after Minkowski came up with it. But the problem with Minkowski, he couldn't tell the difference between the right-angle triangle rule and in 3 dimensions, that is, right, and the equation of a right circular cone in 3 dimensions and a hyperconoid in 4 dimensions, because he uses one and the same equation, right, for all 3. Well, that's not possible. You can't have an equation for a right circular cone in 3 space, also the equation for a right circular cone in a 4 space. But that's what Minkowski did. All he did essentially was adopt the errors of Einstein and present them in a different format, right? Because in Einstein, he violates geometry. Because in section 3 of his paper, as I mentioned, That's where he says he proves his special theory of relativity by proving that his two postulates are compatible. What are his two postulates? The laws of physics are the same for all moving inertial observers, and the speed of light is the same for all of them, right? And so what he does was he takes a sphere of light. He says, well, we'll take a sphere, expanding sphere of light, and under Lorentz transformation, he's got this expanding sphere of light. You know the equation for a sphere of light, x squared plus y squared plus z squared equals c squared t squared, right? Where ct is the radius. Speed of light times the time. It's growing. So it's centered at the origin. And he says under the Lorentz transformation, I get another set of equations. He did it in Greek letters, but it's a bit harder to say, but we'll use prime letters. We'll say x prime squared plus y prime squared plus z prime squared equals c squared t prime squared. And he concludes, because that equation is invariant, form invariant under Lorentz transformation, it must also be a sphere in the other system. Well, that's not true. If you plot some points, you find that it's not true. You get an ellipse. If you get the equation, if you calculate the equation of what you get in the other system, it's an ellipse. And you still have the equation for the right triangle, because that always gives you the distance from the origin of coordinates to the wavefront. So all Einstein did prove, right, with his section 3 and his Lorentz transformation, all he proved is that the distance from the origin of coordinates to the wavefront is always given by the right triangle rule, the theorem of Pythagoras. We know that from school, right? 2 dimensions and 3 dimensions. He's using 3 dimensions. So that's all he proved. But because he used that equation to describe a sphere of light, expanding sphere of light by construction in his stationary system, and the equation comes out the same form after Lorentz transformation, he assumes that that equation must describe a sphere as well. No, all he's proven is that the distance from the origin of coordinates to the wavefront is always given by the right triangle rule. Give me the equation of the geometric form in the other system. Because when you get the equation for the other system, you find it's an ellipse. But the distance from the origin to the wavefront is given by that same rule, because the ellipse is no longer centered on the origin of coordinates, where his sphere is constructed in his stationary system is symmetric on the origin of coordinates. So in the moving system, it becomes an ellipsoid, not a sphere, an ellipsoid with a moving center of symmetry. And we know
this from like Doppler shifts too, right?
Yes, you can think of it like that if you like, because it gives you a kind of an analogy. But the point is, the equation from the origin of coordinates to the wavefront is still the right triangle rule. And because he's got the right triangle rule, he thinks it's still a sphere over there as well. No. All you've proven is that you've proven that the distance from the origin of coordinates to the wavefront is given by the right triangle rule under Lorentz transformation. That's true. But does that mean that that equation also describes a sphere in the other system? No, it doesn't. Give me the proof that it's a sphere. He hasn't. All he's got is this equation for the distance from the origin to the wavefront. Because you can take any wavefront or any curve in space, the distance from the origin to that curve, whatever its shape, is given by the right triangle rule, right? So I can have a wiggly line in 3 space. The distance to any point on that wiggly line, that curve, is by the right triangle rule. But so if I do a transformation, or if you do a transformation from some geometric form and you get the same equation in the other system, right, from the other system, does that tell you that the geometric form hasn't changed? No, it doesn't. It just tells you that the distance from the origin of coordinates to the wavefront is always given by the right triangle rule. It doesn't say anything about maintenance of the geometric shape. And I've shown in my video, my latest video, that it's an ellipsoid. And Minkowski made the mistake of thinking that C times T is a 4th dimension. No, it's not, because T is a scalar parameter for the distance from the origin to the wavefront. It's a scalar parameter. And having a scalar parameter doesn't make it a new independent coordinate for a 4-dimensional system. Similarly, the right triangle rule tells you that r equals c times t is actually the distance along the hypotenuse of a right triangle. Yeah? So, is the hypotenuse of a right triangle perpendicular to the XYZ axis? No. So it's not another coordinate. It's only a distance between 2 points in the XYZ system. So t is a scalar parameter. Minkowski takes c times t and turns it into another coordinate. Well, he can't do that. And the other problem is he calls that equation, the same equation, a four-dimensional cone. Well, I've proven that no, if that equation is to be used to represent a cone, right, it is a cone in three space because t still remains a scalar parameter. And you can eliminate the scalar parameter and you get the usual equation for a right circular cone in three space. So it cannot be an equation for a cone in three space and the same equation as a cone in four space. You can't do that. You have to have a separate equation for that with four independent coordinates. So Einstein made a blunder. Minkowski copied his blunder and presented in a different format. So both of them are wrong, which means that the two postulates of Einstein are not compatible under Lorentz transformation at all. But that's the core of his theory. Without that, he has no theory. Since it's false, his theory is false. This is a question of pure geometry, right? And I've covered that in my lecture and in my associated paper. So if any people who are listening or watching would like to see this and how it works, it's a bit technical, right? But they can see it in my other video on Sky Scholar, and they can read my paper. I call it the Lorentz sphere. It's available online for free as well. So all the details.
What isn't technical is the basic understanding that if I'm going to go and measure this table, which is what geometry means, right? To measure, originally to measure the Earth, but to measure an object, right? If I'm going to go measure this table, I don't need a clock. It's just absolutely unnecessary. It clearly has nothing to do with measuring this object. And to ascribe some characteristics to the geometry other than the evident degrees of freedom that are present in any body, in other words, the length, width, and height, is not. It doesn't compute. It's a broken logic to begin with to roll these things into one conception. And I don't think that you need very complex math to come to that conclusion.
Yeah, I like being able to put it in simple terms like that because otherwise it's easy to get lost in the various mathematical transformations that are invalid.
Of course.
Rather than just saying that the fundamental premise of treating time as a necessary factor in measurement of objects.
Yeah.
I like that.
But hey man, and I think we've done more than 3 hours here. I feel like we should get some closing thoughts from you. I mean, I'd love to have you back, Steve. It's always wonderful to talk to you, and I just feel like you're overflowing with ideas about these things. I honestly think we could probably talk for another 3 hours, no problem.
I would love to. I would love to see our next conversation include highlights of people's ideas that you think are on the right track. Because if we have to get rid of Einstein, which seems plausible and reasonable given all of the issues that you have with him, it would be cool to see if there was anybody who is actually working on stuff that you think is headed in the right direction, even if it's maybe not there. And I know that Pierre-Marie is one of those people, but I would love to be able to highlight an entire ecosystem of people that are doing that.
Yes. Well, that'll be fine. I'd like to do something like that. Today was just really an overview of the fantasies that have now permeated modern science and turned it into this mystic thing that we call modern physics and cosmology and astronomy. I think it really needs to be overhauled. And Pierre-Marie Robitaille is doing a great job on resetting astronomy on a proper course by having a proper model of the sun and the stars based on physical evidence. He's not using mathematics here, making up theories and all of this. So this is a question of physical evidence properly analyzed and acknowledging, which the astronomers refuse to do, acknowledging that there is chemistry in the sun and stars. It's not just your hypothetical physics and trying to fit things to your simple misguided ideas. Chemistry is happening in the sun, and the physical evidence proves that it is not a gas. And you cannot have a model of an ideal gas and have it compress itself to raise its own temperature in violation of the first law and use the kinetic theory of an ideal gas where there are no gravitational forces by hypothesis between the particles, and then add gravity between the particles and get nonsensical expressions like Mr. Parker does, where he's got gravitational potential energy affecting the temperature of the gas. Well, that's not true. Here's an interesting thing before we go. In 1896, Ludwig Boltzmann, he's a smart guy, Ludwig Boltzmann, he proved that if you take an ideal gas in a container at equilibrium and suspend it in a gravitational field, you will have a pressure gradient, a density gradient, but the temperature is the same throughout the whole gas. There you go. So gravity is not going to change the temperature of the ideal gas. And that's in 1896 in his book on gas theory. Very interesting and simple deduction from, when you look at it, it's simple enough, but he thought of it and demonstrated it using the ideal gas equations. Right? So there you go. Interesting.
He also hung himself.
Yes. He had a lot of problems with people stealing his work, fighting against him, and he lost his tranquility. So
It's tough being a scientist.
Yeah. Because he was suffering a lot of ridicule and people stealing his work. Planck had no problem about using things of Boltzmann and not crediting Boltzmann. He did it all the time. You know? So it's not good.
Well,
Anyway,
I really hope we can get Pierre back out here soon. He keeps promising to do another one, but keeps pushing back the dates. So maybe you can put a little squeeze on him next time you talk. We need to get him out here. Last time, we had a different format for the show, which wasn't appropriate. So
okay.
let's get
I'm
him
sure
back
that
out
he's got
here.
a lot more interesting things to say than I, because he's got a lot more material and he's got a good working theory and all. And mine's just a hobby. So
it's a joy talking to you, Steve. It's really the passion that you have for the subject really comes through, and you're so patient and willing to explain and to stop and to put into context. And I think that's really valuable for the world. And so thank you for taking the time.
Oh, well, thank you very much for the invitation. And I just hope that some viewers and listeners can make some sense out of what has up to now been quite a lot of nonsense coming from the scientific community.
I think better after this conversation than before.
Yeah. As Newton said, but just before he died, he said, when he was going to leave the world, he said, well, I hope I leave the world, philosophy in a less mischievous condition. So there you go.
Nice.
Yeah,
all right,
well,
Steve, thank you so much, man. It's been really good to hang out with you this morning. And I think we should do it again down the line. And there's just so many sucker trails we could dive into.
There's a lot of things we could talk about. Yeah, but I think Pierre Marie's a good interview because there's so much material that's very important. All I'm doing is really showing that these other things are wrong, but he's giving something new, something different, right? So even though we've written a few papers together, his work is sort of original work on new theories. Right? I don't have that skill. I don't have the skill for making new theories. I'm just looking at things. Is this logical? Is this logical? No, this is not logical. It can't be right. But I can't offer any new theories, and why should I? You don't have to make a new theory because you find something's not right. And that's
where it all starts from.
I think that's what collaboration is for too. I think that there's teams that work together where people are bringing different skills to the table, and someone who's able to conceptualize needs a mathematician because math is the language in which these things are accepted and discussed. And so the two of you together are really a force to be reckoned with.
Oh, well, thank you very much. Yeah, thank you very much. Well, I think we've made a good team on what we've written together so far. So I've had the privilege of writing with him, and I appreciate the opportunity of writing with him. He's a great scientist, and so we have done some nice work together. Maybe we'll do some more down the track. Who knows?
I hope so.
Anyway, thank you very much for your time, and I hope you have a nice day. And your video comes out really nice, and I'm looking forward to seeing it and listening to it and passing it on to people who I think might be interested as well.
Excellent.
Me too, yeah. All right, good night,
Okay.
Steve. Get some rest. It's quite late there.
Yes, it's 7 a.m. now. I've got to go to bed yet.
Well,
All right.
All
sleep
right.
well.
Good night,
Thank
Steve.
you very much. Yeah, bye-bye now.
Bye.